And at the end, at 2:30, at least according to the schedule, we'll have time for discussion. So we've allocated about half an hour for discussion, so we will try to be a little more organized about making sure we have time for discussion today at the end. So with that, why don't we go ahead and, well, we're 3 minutes early, but I think it's okay if you start, Vince.
Okay, can you hear me?
Yes.
Okay, let me try and present this. Can you see that?
Yeah. Yep.
Okay, maybe that's good enough. Okay, yeah, well, thanks for giving me the chance to talk here. I'd like to talk today about RegTune, which is a regional tuner for global atmospheric models that's being developed by Jun Guo and myself. So can you hear me and see the screen well? Am I speaking loud enough?
Yeah, we can hear you.
Okay, thanks. So by tuner here, what I mean is a parameter estimation tool. So a piece of software that will optimize the values of parameters in a model like CAM. So first I'll ask the question, why tune? What do we expect to get out of a tuner? What insight do we expect to glean? Then I'll ask, how can we reduce the cost of tuning? Then I'll discuss some typical tuning problems that model developers face. And finally, I'll show some example tuning results from a global model. So first, why tune? Oftentimes, when we improve a model's formulation, in other words, its structure or its equations, the results get worse. They get worse because an error that was compensated formerly by a different error is no longer compensated. So when that happens, we want to retune first in order to restore the accuracy of the model. But then in addition, we want to get hints about what part of the model structure is still wrong, what part we want to change in order to make it better. And we want to retune as quickly as possible so that we can resume working on the model structure, on the physics, instead of endlessly twiddling parameter values. So how can we reduce the cost of tuning? Well, by reducing the number of global model simulations. So a lot of tuners require 100 or more global model simulations, which is expensive. And we'd like to get away with as few as a couple dozen. And RegTune does this by using a crude approximation of the cost function's parameter dependence. Namely, we just assume it's a simple parabola. So in parameter space, we're just going downhill to the bottom of a parabolic valley, and that's it. So to find this parabola, RegTune expands the model's parameter dependence in a Taylor series. So the user decides which regions he wants to tune, say a stratocumulus region, a cumulus region, say a warm pool region. Can you see my cursor when I move it?
Yes.
Okay, good, thanks. And the model predicts some field, say cloud cover, denoted by F here, and we want to match the OBS in the corresponding regions. And we want to match it by tuning these parameters P1 and P2. And we hope that by breaking the tuning process into these sort of different regions explicitly, that will give us some insight into the model error. So RegTune uses a Taylor expansion. So we start with a default simulation with the default values of the parameters. And then we adjust the parameter values in order to better match the observations. And doing so introduces this sensitivity matrix. So the first column is a sensitivity to the first parameter. So it gives the change in cloud cover, say to the change in parameter P1 for the different regions. And then the second column is the sensitivity to the second parameter. And RegTune also has another term here, the diagonal part of the quadratic term in the Taylor series, which is important for regularizing the solutions, but we won't describe it in this talk. So instead, we'll just keep it simple. We'll move this default model solution to the right-hand side. We'll ignore the nonlinear part, and then we just have this very simple matrix equation. And one can view the tuning process as basically trying to represent this bias vector. So this here is the model bias, the default simulation minus the obs. Represent that as a linear combination of the columns of the sensitivity matrix. And the weights of those sensitivity vectors are simply the parameter adjustments. And you can see the problem here. So we have two sensitivity columns, two sensitivity vectors that spans a two-dimensional space, in other words, a plane. But the bias vector is three-dimensional because we have three regions. And so more likely than not, part of that bias vector will be orthogonal to the plane spanned by the sensitivity vectors. And that part of the bias, the orthogonal part, is not removable by tuning. That part, the existence of that part, is related to the model structural error. And that's the part that we want to understand better so that we can fix the model. So, we can approximate this matrix by running some global simulations. And we can also approximate the bias vector, and the parameters here is the only thing that's unknown. Okay, so let me walk through some examples of what it's like to be a model developer, day in the life, or maybe a month or a year, depending on how much time you waste tuning parameters. For simplicity, I'll reduce the problem even further. In this case, I'll just have one parameter here and two regions. And the tuning problem here basically means scaling the sensitivity vector by the parameter value so that it matches the bias vector as closely as possible. So the most standard problem is a tuning trade-off. So again, this is our sort of system of equations. We can represent it in various ways. This way here is pretty simple. We plot the observed value, which is related to the bias for each region, versus the sensitivity, which again is this vector. So we imagine we have a stratocumulus region here, which is not very sensitive. So this matrix element is small. Cumulus region maybe is more sensitive, and the stratocumulus maybe is supposed to be bright, and the observations cumulus is dimmer. And the model, let's say, models stratocumulus correctly, but then overpredicts cloud cover in the cumulus region. And so what does tuning mean? Tuning means rotating this line here so that it better matches the cumulus while still passing through zero. But in doing so, of course, we make stratocumulus worse. So we can show that in this other type of plot where the initial bias in stratocumulus and cumulus, stratocumulus is correct, no bias, but cumulus is too bright. The model simulation is way up here, the actual obs are down here. Tuning can reduce the cumulus bias down to here, which is good, closer to the zero bias value, but the stratocumulus then is pulled away from the correct answer, and it's made worse. So you get some sense of the model structural error here. Basically, the sensitivity vector is dimming in both regions, but in fact, we only want to dim in the cumulus region, not in the stratocumulus region. And another way of looking at this is just to plot the sensitivity vector, here it's in green, and plot the bias vector, here it's in orange. And if they're not parallel, well, then we can't remove all the bias. Basically, we can only remove the part of the bias that's parallel to the sensitivity vector. The residual bias, the existence of that is due to the model structural error. Now, a stubborn bias is similar. It just means that we have a region which has little sensitivity and a very large bias. And the symptom when we're tuning is that we start with a large bias and we just can't budge it. The bias is just very stubborn. So in that case, we either need to find a new parameter or change the model structure or something. But you can see here, if we rotate this line up to pass through the stratocumulus, it's going to way over predict the cumulus cloud cover. Okay, so now I'll show some example results from a global model, E3SM. We have 8 club parameters. That means we need to run 2 times 8 plus 1 for the default global simulations. So 17 simulations, maybe 2 days in the queue. We want to match shortwave cloud forcing in various regions. So Hawaii region, for instance, or maybe near coastal Vocals region for stratocumulus, maybe near coastal Namibia or far coast Namibia. We also want to match the globally average long wave cloud forcing and the surface precipitation. So we can make some simple plots. Of course, it's harder to visualize in high dimensions, so that's part of the problem. But we can make an analogy with this simple sort of plot. And what we can do is plot the bias on the vertical axis. So this for each region, and plot it versus the magnitude of the sensitivity. So basically that's the magnitude of this row vector. So it's the overall sensitivity with respect to all parameters. We plot that for each region, and then we get a plot that looks like this plot. And we just want to kind of pass a line through it. But you can immediately see that these two regions, long wave cloud forcing and PREC T, they have a strong bias and just very little sensitivity. So we're just not going to be able to budge them. So we might as well forget about those. Now, treating this like a simple 1D plot is very hazardous because we're ignoring all the correlations between these rows in the sensitivity matrix. But let's just, for the moment, assume we're going to do that. Then we see that Hawaii has a very strong bias, but a very large sensitivity. Because there's a large sensitivity, we might hope that we can run a line through it, remove the Hawaii bias, and maybe also improve the Namibian bias. But then we have these other regions, these near coastal stratocumulus regions with an opposite bias. So Hawaii is too bright, near coastal is too dim, and it's looking like we're not going to be able to remove both those biases in a simple way. However, let's see what the tuner says. The tuner will go and it will do its quadratic fit. It will find some parameter values, and it will also predict how the biases will be removed in various regions. So for instance, it says we can remove the Hawaii bias and the Namibian bias. So that's good news. This plot is kind of like this plot where we start off with large biases here and then they're pulled toward the 0 line. And it says we can do that without damaging the near coastal regions, which is a little surprising because this plot seemed to suggest that there's a tuning trade-off. Any case, Jun ran with the recommended parameter values, and what he got was these red arrows here. So the good news is, yeah, the Hawaii bias actually was removed. That's nice. And the Namibian bias was removed too. But then these near coastal regions, which the tuner claimed would not be damaged, were in fact damaged. They were made even dimmer. So this is sort of our experience with this tuner. It's very primitive and simple. It gives you some useful information, but it doesn't give perfectly accurate answers. The thing I like about it is it gives more information. So let's look in more detail at these near coastal regions. We can break down what the tuner thinks the bias removal contributions will be due to each parameter. So what it's saying here is in these near coastal regions, the tuner thinks that this parameter N2 thresh, which you don't have in CAM6, so don't worry about what that means, but that's dimming these layers, which we don't want, but that this other parameter altitude threshold is brightening the near coastal layers and that they should be compensating. Well, in fact, we see that they're not, but the fact that the tuner is honing in on these particular values is useful and interesting to me because both these parameters deal with damping fluxes in stably stratified regions near the surface. And you can see why that would be important for near coastal stratocumulus because near coastal stratocumulus have low cloud tops. If you don't damp the fluxes properly, you'll get too much cloud top entrainment and they'll go away. So it gives you some hint of where to look next if you want to fix model errors. So in conclusion, yeah, RegTune can help speed up the process of tuning. It requires only 2 times the number of parameters plus 1 global simulations. It tells us which parameters matter for which regions, which can in principle give you some hints as to how to fix structural model errors. So thanks so much.
Yeah, I have a question about how you sample the parameters. So you're only using 2 values for each parameter. How do you determine those? Is it like a bounds, like a min and max value, or how is that determined?
Yeah, not very quantitatively. So basically we have our default value and then we perturb up and we perturb down, and that's just basically based on physical intuition. But you're right, if we choose parameter spread that's too wide, well, then we're in regions that are unphysical. If we choose it too narrow, then we don't see any possible curvature in the parameter values. So I don't really have good advice on how to do that.
Vince, what happens, in your example, you have a small number of parameters, but for example, in the CAM6 PPE, where we are just looking at the cloud-related parameters, we have 45. Does the number of simulations you need goes as 2 times the number of parameters plus 1? So if you have 100 parameters, does the cost of the tuning actually explode to just as much as hand tuning?
Yeah, so it doesn't work well if you have a large number of parameters. So I guess this tool is basically designed for like a model developer who has some understanding of the physics and who really wants to work on the model structure, but just needs to quickly retune. And the idea is that there's, a few parameters that you want to play with to improve a few regions of the model. But yeah, in your circumstance, yeah, you need something more sophisticated. This is a pretty primitive tool.
Okay, thanks.
I have a question. Hi, Vince. This is Adam.
Hi.
I'm interested in these parameters like C11B, which are skewness dependent parameters, meaning C11B would be a damping coefficient that we would only apply if there was high skewness. I'm also seeing a lot of these N2 stability modifiers in these nameless names. Are they doing a similar thing where we activate these nameless only when it's stable? We have to activate these coefficients only when it's stable?
Yeah. Yeah, that's a longer discussion. Yeah, that's sort of a technical question that we should discuss at length. The parameters are not doing the same thing. Basically, my feeling is at this point, Club has too many parameters. We're trying to get away from some of the skewness dependent actually, and move towards more of these stability based. But right now, both sets of parameters are in the model. So yeah, let's talk about that in more detail.
Okay, thanks, Vince.
So Vince, there's no attempt to do cross correlate, change 2 parameters at once and figure out second derivatives or things like that, right? In derivatives of 2 different parameters.
Exactly. So basically, in this quadratic term, we only keep the diagonal part. So those interaction terms aren't there. Yuan, Chen, and actually Jun have both studied those interaction terms, and then they do matter in some cases. It can be like 10%, 15% error that you get from neglecting them. One thing you could do is use this type of approach, but just take small parameter perturbations. The interaction terms will only be important if you make a larger parameter change. So you could, use this iteratively and then just move one little step and keep moving steps, ignoring the interaction terms. But yeah, I think you bring up a good point. I'm guessing that that's the problem here, that the tuner made a wrong prediction because these terms are actually interacting because they're both sort of governing the same part of the model, and that interaction isn't included in the quadratic function.
Okay, so that means that the basic information for this is really those sensitivity vectors to each parameter.
Yeah, okay, there's a part I didn't talk about, which is the diagonal terms. A lot of the dependence, and this surprised me a bit, is not linear. In other words, there's like a strong parabolic change. So in other words, you take a default value of a parameter and you perturb it high, perturb it low, and both solutions say are worse than just keeping it the default.
Mm-hmm.
It's not a linear change. And that's been very interesting to look at. And I think it's part of the reason why, parameters like gamma coefficient historically have been very effective, because those are very linear. A lot of these other parameters, they're just nonlinear. And so it's hard to get a feeling to predict how the model will behave when you change them.
All right, thanks. I think we should, thanks Vince. I think we should move on to the next talk.
Thank you.
Our next talk is from Colin Zarzicki on an emulator.
Yeah.
Oh,
you're
right.
I can pantomime.
I can't get onto the computer here. Hello. Okay.
In the opposite way. Oh, sorry.
There's the mic.
Sorry. This one here, that is mine.
All right, well, thank you very much. Actually, this falls on pretty nicely to what Vince talked about. In gray is like the actual title that I gave Julio 3 months ago or whenever we had to do this. And then really the secret title is mostly this was good motivation for me to mess around with code. And I do like touching things, so this is like my good reminder that I need to not touch the screen. So usually the last few AMWG meetings, I know I've been talking, giving an update. So a lot of this work is coming out of this Momentum Flux CPT where we've been kind of implementing these updates to Club with an eye towards CAM7. So I just want to have a couple slides, just kind of what's really motivating this. And so primarily, I know Julio's mentioned this a couple times. We've talked about these CPT improvements to the boundary layer to really Club in CAM right now. And the two improvements or the two updates we've implemented are directly prognosing momentum fluxes. So we're not using an eddy diffusivity closure here, but we're actually going and using the Reynolds average equations to predict momentum fluxes. But what's perhaps a little more relevant for what Vince talked about and what I'm also going to talk about is we also have a new way of kind of essentially estimating turbulent length scales or turbulent dissipation in different layers. And this is colloquially, this bottom equation is known as kind of the Tau's formulation or the Tau's code. But quite simply, what we're just going to say is that we have some new coefficients that go into this term, such as like the N2 term that was mentioned in the previous talk, that helps kind of give us some more generalizability or modulation of turbulent dissipation, depending on what the structure is of the layer that we're interested in. So, and I also showed this slide before, but one common question is, okay, well, we're introducing additional equations to Club. If anything, what we're doing is just adding more of these tunable parameters. Is that a problem? And the answer is hopefully no. So the way that we've implemented these updates in the CPT framework or on CamDev is that we've really traded parameters. So we've added new parameters, but we've also removed a set of parameters so that we've not made the problem any larger. I mean, it would be nice if we could make the problem even smaller, but at the very least, it's not any larger. And then the hope is, especially with this Tau's code, that we have a lot more kind of control over understanding at the process level what is going on inside of Club and kind of how are things like momentum fluxes behaving differently in different layers. So what really motivated this idea of thinking about kind of using this really, really high dimensional data set to try to constrain or understand how these new parameters are interacting within Club or how they're behaving. There's a paper by Yun Zhan in 2018, and this figure is actually buried kind of toward the bottom or the end of the paper. It's probably like figure 13 or something like that. But really is pretty interesting to me. And what they found is that if you use 3-day short-term kind of hindcast initialized runs, and then you look at how different metrics are changing, so example, the convective precipitation, and how that responds to changes in certain tunable parameters in CAM, that you actually get a fairly reasonable approximation of what actually happens in a 5-year simulation. So at least with regard to fast physics errors or fast physics evolution, short-term simulations can provide us with a great deal of information that we would also see if we were to run like a 20-year simulation and then look at the AMWG, or now the ADF diagnostics package. So my one advertising slide on here. So we're going to talk about initialized runs in CAM. Have a software package that has started to grow. It's still written a lot in NCL, so I apologize for that. But we have kind of this new infrastructure that allows you to quickly kind of initialize the model with observations or reanalysis. It has things like hydrostatic adjustment to balance against different topography files. There's now code in here to generate data atmosphere files for spinning up the land model. for generating nudging files, for nudged experiments. So anywho, if you're interested in anything that leverages reanalysis for actually running CAM, come talk to me. I always like talking about these kind of tools. But what I want to talk about today is how do we use, or how could we use initialized models to kind of build up this data set to tell us something about what's actually going on, when we change something like this, N2 parameter or something like that. And so what we're going to do is we're going to create a set of P parameter inputs and ranges that we're interested in. So I've just kind of built here a long list. Obviously, most of this has some of these new club terms in there from the CPT. But I've also included a couple other ones from John McFarlane. I actually included one from the DICOR just for fun. And the idea here is what we can do is we can define a parameter and then give it some sort of range. And this is the range that we want to sample in the model. And then what we're going to go do is we're going to go generate a Latin hypercube kind of sample. And we're going to define what this sample is. So we're going to say, I want to run 1,200 iterations or 1,200 configurations. And what essentially we'll do is we will go and pick kind of combinations of all these 23 parameters that try to fill that 23-dimensional space as effectively as possible. And really the output of this strategy is going to be, okay, we're just going to get a text file, and this text file is going to have 1,200 lines in it, and then each one of these lines is just going to be a CSV that has 23 different parameter input combinations that we can pass into CAM. And then what we're also going to do is we're going to say, okay, well, we're going to try to leverage these short-term initialized runs. What we're going to do is we're going to run 6 of them for each of these 1,200 experiments. We're going to initialize them on the first day of January, March, May, July, September, November, just to get some sampling of kind of the annual mean. And we're going to just run each of these simulations just for 3 days. That's all we're going to do. So we're going to end up with 7,200 simulations to run. But they're only 3 days, which is nice, and we can kind of parallelize this on Cheyenne. To be honest, the real world throughput's not bad. We get about 3 to 4 real days if we spread, or it takes about 3 to 4 real wall clock days if we spread this out kind of across like 20 helpers that are initializing these runs, because each run only runs for a few minutes. The other nice thing is, since they're pretty small, they're really easy to kind of backfill in through like the economy queue or help optimize and fill space on Cheyenne. And then what we're going to do is we're going to take the outputs from these fields and we're just going to average them over 24 to 36 hours for a variety of climate metrics. Currently, right now, I'm just aggregating these to 5x5 grid boxes, although that's more of a practicality just to make my life a little easier and to reduce the size of these files a bit. But at the end of the day, what this really gives us, if we do this 5x5 grid boxes with these 1,200 outputs, it gives us 2.7 million points to kind of see if we can understand something about what is the climate signal in these simulations. So the tool we're going to use here is we're going to use a random forest regressor. Now, admittedly, I've tried some other things, and I'm sure there are pros and cons to different reasons, or pros and cons to different techniques. So essentially what we're going to do here is we're going to have an ensemble of these kind of decision tree-like things, and we are going to try to predict at each one of these grid points based off of these coefficients, what is the response of some other kind of set of combinations that a user is interested in. And the way that I have this coded right now is that you actually just have a user NLCam file, just like you would have if you were actually running the model. And you could go in and you could say, I wonder what happens if I change club CU buoyancy. And I'm going to try to understand what happens without actually running the model. So this emulator is done completely offline. The other thing I just wanted to mention, and this is one of the benefits of using something like a random forest regressor, is it does give us some information about feature importance. So kind of like what Vince showed on that slide where you're trying to look at the directionality, but also the importance of how different terms contribute to different responses. So what I've actually done here is just dumped the feature importance for these different, 2 different variables, low cloud fraction and precipitation. But the nice thing here is there have been some other papers that have done a sensitivity analysis, and then my student Kyle is going to also talk a little bit about this later. And what you find is that the regressor actually matches very well with what people have done previously in literature using things like generalized linear models or the Morris method. So this is just one example, the last couple of slides here. I want to show one kind of example of how this would work, but essentially, let's say we have the default CAM6 configuration, but we have these biases. And let's say someone ran the ADF package and they're like, oh, this is the Strato Q decks are too bright or something like that. Is there a way that we can reduce that? So we can go in and we can edit our user NLCam file offline, change some of these settings, and then what we can do is we can run it through the emulator and see what happens. So remember, this is the emulator that's trained on those 3-day simulations, and we've just changed some knobs, and this tells us roughly what should happen to the shortwave cloud forcing field. And then what we can do is we can go verify this against the atmospheric model, an actual like a 10-year simulation, and I've highlighted up there the global mean response in shortwave cloud forcing that's predicted is 1.7 watts per meter squared, and then in observation, or in the actual 10-year run, it's 1.18. So, not perfect, but the directional response is kind of there. We could also do the same thing for sea level pressure. So if you're changing a lot of these momentum terms, we're probably changing the mean sea level pressure, but also the distribution of the mean sea level pressure. And then we can see that we reduce the global mean sea level pressure by a tiny bit in the emulator, and we see that same response in the 10-year simulation. But what's also interesting to me is we're starting to see some hints of some regional structure here. And this I caveat, like I have not looked at this too closely. I had grand plans before all of my household got norovirus or something last week to start to look at this before I got here. But you can start to see that the emulator is saying when we change these settings, we start to get this general increase in sea level pressure kind of in the tropics and the mid-latitudes, and this decrease kind of at higher latitudes. And that response is also seen in the long-term climate simulation as well. Just a quick note here on the cost. Once you actually get this deck, I think this is pretty reasonable and pretty cheap. Like I said, it's really to generate one of the training data sets for this. It's essentially the equivalent of running a 60-year FCOM set simulation. And then right now, this actually runs pretty trivially on just a local machine. I'm just doing a lot of the dev work on my MacBook, but you could very easily kind of run this on Casper or something like that. And depending on what model you're using, whether this is like the random forest regressor, obviously you can imagine situations where maybe we could use like convolutional neural nets or things like that. They'd be a little longer to run, but this is certainly much more feasible or tractable than running multiple 20-year simulations and looking at the output. So this is just my last slide. So first blush, what we've been looking at so far, pretty much everything we've seen across the board is this is really good for global mean directional signal. So if I'm interested in, I want to increase the amount of precipitation in the model, this seems to get you that answer pretty easily, unless you have like a very kind of small increase or decrease in that. It's not too bad for global mean magnitude, obviously. Without allowing for nonlinearities or long-term adjustment in the climate system, I don't think we'll ever get to a situation where like the magnitude is spot on, but I think it's in the ballpark. The one thing I haven't looked too much at is there's some hints maybe that there's some regional information, but I think that needs a little bit of work. There's a lot of next steps here. I think really the question for the working group is going to be, how do we better leverage some of these kind of short-term runs, these initialized runs? I know the DOE groups have kind of been trying this as well over the last few years, but I think there's a lot of capability here to kind of better optimize and make better use of our resources. And the other thing is, like, as and Vince kind of mentioned this, I think there's some space with understanding these initialized runs because you're constraining the initial conditions. You're giving it something that is akin to a numerical weather prediction model. I think it probably opens the door for some degree of physical interpretability and like comparing to actual observations, soundings, and things like that could be useful. So with that, I think I'm pretty much at the end of my time. So.
How did you pick the 1200 number for your 23 parameters?
Good question. Not very quantitatively. So there are some metrics that come out of the Latin hypercube sampling. So we can kind of get some indication of how well it filled the space. But when I benchmarked all these numbers out, 1200 seemed reasonable to get things through in like a week, in the queue. But I think exploring whether that number should be bigger, whether that should be smaller, isn't on the table. The other thing is with the 6 months that we use, originally I was thinking about using 12 months, but I don't know if there's any improvement there, if we can get away with even shorter than that.
Yeah, I'd be really interested in seeing like if you took a subset of 300, 400, 600, how your error values in your random forest would look
Yeah, so that's really what I should do is bite the bullet and make like a giant data set, and then I can subsample and see how
Yeah,
that
yeah, because our
works.
PPE has like 45 parameters and 200 and something simulations, and you have so many more that I feel like you have a test bed for looking at this question.
I did not do that. So.
Yeah, Katie and then Jesse?
Okay, thanks, Colin. Maybe related question, but looking at I'm curious if you looked at the spread in the responses across, say, a single initialization across the 1200 set. How does that compare to a single parameter set across the 6 initializations in terms of the quantities that you're interested in? Like, how much spread are you getting from those 2 different sources of variation?
Yeah, that's a good question, and to be honest, I will admit that I have not looked at that. So the 6 initializations in the pipeline that I have currently just get pretty much like glued together and treated as like a global mean, almost like a climate simulation response, and that's been the idea. I have not tried to like pick at what the individual responses within that 6-member data set before I do that averaging, what they're actually doing. And that's actually a bit of a concern of mine is that like you could have one simulation that has like a really strong response in a given season, but then in the other iterations, if you don't have that response, then the model looks at this and says, well, there's no response there, or it's very small. When in reality, that might be a nonlinearity that we're missing, so.
I'm just curious from the throughput question, so it sounds like, so did you end up like building the model 20 times, so you had 20 different jobs, and then just change the username list 60 times per each to?
Exactly, yeah, I just cloned with the keep.exe, so it's actually using the same binary, and then everything here, if it's in user NLCam, it's super easy, it's just a sed script that just pipes it right in, and if it's not in user NLCam, just make some source mods to let it be a tunable nameless parameter,
Right.
and then it's, yeah, exactly.
And then I assume, yeah, and then, sorry, was each just doing like kind of one node, like how much total?
I'd have to look, I think I run them, it's the 1 degree model, so I probably run it on something like 4 to 8 nodes
Okay,
or
but
something.
you're not like asking for 1,000 or something.
No, I mean, one thing, if they did like a discount, like DOE Metal does, like you could bundle them and things like that, which would also be reasonable. But I think for this, just kind of pumping it through. At any given time, there's like 20 things in the queue, so it's not
Right,
too
yeah.
bad. It's not like I have 1,200 in the queue, but yeah.
Okay, cool, thanks.
Thanks, Colin. Oh,
Just want to mention, because people cannot see when you are pointing to the screen, the online people.
Oh,
If people can use the mouse.
apologies.
No, it's
I was
fine, yeah.
trying to be good and not touch the screen.
thanks, Colin. I think, yeah, we'll go to the next talk now.
Yeah. Hello?
I can go wherever you want.
You gotta turn it on.
Oh, yeah, just wait to turn on and just a little higher. Yep.
Oh, yeah.
Oh, yeah. Awesome. And then I can go wherever, just right here. So, just go ahead and put it in the file.
Okay, so, can you hear me? We're kind of doing some of the same thing that you have done. So, our motivation is, well, we want to understand the sensitivity in CSM for all these different parameters. And we also want to understand some of the climate sensitivities. And also we want to look into if we can use this perturbed parameter ensemble to maybe tune the model. So basically the initial goal is what I just said. I think, well, we want to look at the mean state climate, but also the forcing and cloud feedbacks. And we decided to run this perturbed parameter ensemble with the Latin hypercube sampling. And I'm going to go just simple explain it for anyone that hasn't heard about it. I learned it just a few years ago. So, so when we run the PPEs, we can choose to maybe just change one parameter at a time. And if we want to have big combinations of all these different parameters, we have to have maybe up to millions, several millions of simulations. But we can sample randomly instead. So when you sample randomly, like here, you have just 2 parameters, but we want to have all combinations of those 2 parameters. So here you can see that if we just randomly sample for parameter B, the value is the same for 2 of these parameters, or 2 of these samples. What Latin hypercube sampling is doing is that makes sure that all combinations are different, so that parameter B will not have the same value. So there are going to be 4 samples, and all the values in B are different, and the same in parameter A. And that is what Latin hypercube sampling is doing. So it basically reduces the number of simulations that we need, and we still get the entire parameter space. So here's an example from our runs. We used 43 different parameters. And this is just a 3D out of the 43. So this is just 3 different parameters. And each dot there is the samples. We have 263 samples. And just the colors and the larger symbols are spots that are closer to us. And so this is just a 3D example of how the parameters are lined up in the parameter space. And then what we did, here is a list of all the different parameters we changed. So it's all in the cloud physics. So in the turbulence, microphysics, deep convection, and aerosols. So 43 parameters, we ended up with 263 parameter sets. We ran CAM6 CSM for 3 years. We did try with 5 years and figure out that 3 years we thought that was enough. And the outputs, I mean, so that's the thing. We ran 3 different sets of simulations: the present day, the PD, and then the pre-industrial. And that is with aerosol forcing taken from 1850. So by running these 2, we can get the aerosol forcing. And then we also ran one set with the sea surface temperature increased by 4 Kelvin. And with that, we can get the cloud feedbacks. And for the output, we have close to 200 different outputs for monthly mean states. And then we have 22 outputs for daily averages. So yeah. And then we have put all this data up on, got a DOE for it. So if you're interested, if you are not have access on Casper, Cheyenne, we have them on Cheyenne, but if you don't have access to Cheyenne, you can find them here. So here are some of the results. So this show a few different outputs for the 3 different sets of simulations: the present day, pre-industrial, and increased SST4. And you can see the spread. The solid line is just the mean of each type of simulations. Dashed line is the control rate. The control rate is basically the default parameters in CAM6. And then the shaded line here is the 1 sigma of each different set. So that's 1 sigma of all the 263 different simulations for each of the 3 different sets of simulations. So you can see there's a big spread of results in the output for all these different parameter combinations. And then what we then can do, we can look at how the forcing and feedbacks are dependent on all these different parameters, how the spread of the forcing and feedbacks are within all these different parameter sets. And Margaret Duffy is going to talk more about the cloud feedback from these simulations. And then one of the things that I've been looking at is I want to understand some of the output dependence on the parameters. Which parameters are important for different outputs? And to do that, I've been doing machine learning to kind of increase the ensembles or the sets we can look at to increase the statistics. So here are just some examples of some of the machine learning tools I've been using. So to the left here, these are the test data. So what I'm doing, I've been using a tool from Duncan Watson Paris. He's created a machine learning tool where you can choose what type of machine learning technique you want to use. It's called the climate bench. So we can use the convolutional neural network, Gaussian process, random forest. So you see here that if you just compare with the test data, the climate bench, the Gaussian process actually is comparing somewhat nicely. I'm going to look a little bit more into the statistics. I don't have the results quite now. We also worked with a group from Columbia University, Greg Elsasser's group, and they are using a neural network. And you can see that these results here, they're managing to predict the shape of the distribution fairly well. So all the results further on is going to be from this Colombian neural network. And all the results I'm showing here are just global averages. The climate bench tool, you can get the machine learning in two-dimensional. So what I was interested in looking at, what parameters are important for different outputs. So what I'm showing here are just the black ones are all the different results from a few different, well, I'm showing 3 different outputs: random, shortwave, cloud forcing, and long-range cloud forcing. And the blue lines are all the results from the PPE that we ran. And then the blue line is just the regression line through these results. And you can see there's a big spread of results from all these different parameter sets. The black one is the emulator, the neural network emulator from Columbia. And you can see that the slope here is comparing really well with the simulated ones. Not all of the output parameter combination are that well, but they are fairly close. And then what we can do is that we can look at these slopes. The results with the steeper slope are more, the output are more dependent on this parameter than if the slope is fairly flat. So what I'm going to show here is that this is showing the different output parameter combinations. So these are all the combinations, parameters we have, and here we have chosen a few outputs. Over here we got radiation outputs, cloud microphysics outputs, precipitation, and here are some radiation, some MODIS AOD outputs. And then let's see, up here is the turbulence scheme, club, microphysics, aerosol, and convection scheme. So you can see, like, if we're looking at the cloud forcing, some of the darker colors, both red and blue, they have a steeper slope. So it might be that if we're going to look at cloud radiation forcing, we really want to understand some of these microphysical parameters, and especially its autoconversion, cloud drops to rain, also autoconversion of ice to snow. Ice fall speed is really important for this. If you're interested in precipitation, you want to really understand some of these convection parameters. And these are just global average. And we can also just look at are there other parameters that are more important in other regions of the globe? Like in the tropics, you have some of the turbulence parameter that might start showing up a little bit more. So it gives us an idea of the importance of the parameters. And there are a lot of other different outputs we have. So there might be some other outputs in turbulence that are more important if you are looking into these types of outputs. Then finally get to some of the tunings we just started looking into, like can we use this to tuning? So this is, the red line here is just the CERES observations. And we want to see if can we find some parameters that is showing up that will give us the results close to CERES. So we take all this, so we take the machine learned samples. So I have about 500,000 samples created with a hyperlattic cube. And so I'm trying to find all these samples that are within plus minus 1 watt per square meter and of Povrastom, shortwave forcing, and long-wave cloud forcing. So when I do that, if I first look at shortwave cloud forcing and long-wave cloud forcing, and here I'm just looking at choosing a few different parameters, and these are all the microphysics. So it seems like for shortwave forcing, there are some parameters that are maybe, it doesn't matter what they are, they line in that little region near CERES. You have for shortwave cloud forcing, the fall speed of ice. It seems that there is some values that are more prevalent in that bin. For long wave forcing, it seems like maybe these values here of parameter, it starts to be more favored, but there's so many different combinations we have that it's kind of hard to actually understand this. Here you can put them together, and it still pops out the fall speed of snow on ice that you really want to hone in on that one. And then you can add on Vestom. Do we find some other results here? And this is just something I've just started looking at. So I'm trying to kind of understand how to use this to find what parameter combinations that will give best tuning. So summary, the PPE we have is a good way to probe the sensitivity of CSM physics. We have 3 sets, the pre-industrial, present day, and 4K SST. There are 263 ensembles each. So we have a lot of outputs, a lot of statistics to use this. There's a large spread in the results for all these different parameter combinations. We're working with 2 different emulator tools to isolate the effects of the individual parameters. And we also started to evaluate how we can use this PPE to tune a model. So yeah, so any questions? Yes.
Yes, nice talk. I'm just wondering, do you just take the global averages of these quantities and train on those global averages to give you, for the neural nets to give you a global?
So the Columbia neural network, you have to use the global. The Climate Bench, for this here, I use the global, but you can do the gridded, to train gridded.
Right.
So yeah, the 2D, yeah.
Okay.
Yeah, a nice talk. So regarding your last slide, and I know you kind of mentioned you're just starting to scratch the surface on this. Has there been any discussion or any thought to using something like Neldermead or simulated annealing or some sort of like objective algorithm that tries to like hone in on something that minimizes the error and give you like some example tunings?
Yeah, so the group at Columbia, they have been using some Monte Carlo, what is it, the chain Monte Carlo?
CMC?
Yeah. So they're looking into that, and so we are talking with them and trying to kind of understand what it's telling us. So yes. So.
Oh, I guess if there are no more questions, then we'll take a short break. And we should come back at Thank you very much. We should come back 10.
Yeah.
focus on parameterizing and evaluating clouds, starting with an update on Pumas from Andrew Gettleman.
Thank you. I'm going to basically talk. I'm going to basically talk about cloud microphysics. This is a new implementation, and the reason for this is the new microphysics scheme we're calling Pumas, which is, I'll explain, is an evolution of what we have in the model now. And one of the motivations is you can see the huge cast of people, of characters on here, some of them from NCAR, some of them from other locations. And what I'm going to do is talk a little bit about the evolution. I'll talk about some updates, some ICE nucleation developments, and I'll talk about where this is going, I think, for CAM7 and beyond. So Pumas, what was on the front of the slide, is basically you can think of it as MG3+. It's sort of, you saw from that cast of characters on the first slide, this is more than just Hugh and I, so Morrison Gettleman's not really an appropriate name for the scheme anymore. It's got a lot of changes and corrections to the CSM2 microphysical scheme, and we're introducing a new nomenclature. It now is coming in as an external into CAM. It has its own GitHub repository and is maintained there. There are separate tags there for different CAM versions, and we're also going to start to put tags in there. There's some tags in there for other modeling systems. There's one for the kinematic driver model, and we may start to host some of the other models that it's used in. The new version of the microphysics, the MG3+, is available with the CAM dev physics package. So everything I'm talking about, if you just run CAM out of the box, you're not going to get it. You have to go to the new CAM dev, which is sort of moving on to the CAM7 physics. Otherwise, you're going to get MG2 or MG3 out of that. And MG3 is just MG2 with grapple and hail turned on. If you switch off grapple and hail, it's bit for bit with MG2. So what have we done to Pumas? The options, the things that aren't really on, it still has the grapple and hail option. We're not using that in 100-kilometer simulations. By the time you get to 25 kilometers, not really. By the time you go below 25 kilometers, you probably should turn on the grapple and hail, just as a warning. If you're looking in high-resolution regions, if you're running globally at 14 kilometers or higher, you probably want the grapple and hail. As Bill Skamrock showed yesterday, that's actually pretty critical for getting the right simulations at extreme high resolutions at 3 kilometers. We put in a bunch of switches to replicate processes in the ECMWF integrated forecast system because a version of this Pumas has been put into the IFS for testing for a two-moment scheme. There are now, but those are off, so you don't have to worry about them if you're not interested in doing comparisons with the IFS or running in the IFS. There's open ACC directives for GPU accelerators. Thanks to a lot of work that Jian Sun did, and it actually gives you just a really nice speed up there. We're getting, for the microphysics itself, computationally it's a 10x speed up. There's data offload and back port to and from the GPUs. That slows it down, but if we're running the whole physics package on the GPU and not moving the data, we should get some really big speed up. So I think it shows the promise of that. We put in a bunch of fall speed we put in a fall speed correction for rain, snow, and grapple. Basically, there was an issue where we weren't calculating a fall speed if there was no rain, and so you could get rain falling into a layer where there was no rain, and it would stall out in the microphysics. That was only noticeable at really high resolution and with detailed simulations. It doesn't affect climate. One of the big ones is we've adjusted the ice number limiter. This is independent of aerosols at the end of the scheme. That's resulted in some corrections to the aerosols and the ice nucleation. We've added vapor deposition to snow as a process to be consistent because we have it for ice. And one of the other ones is for, we put in an implicit fall speed calculation as an option for sedimentation and turn that on. That really helps at long time steps give time step stability. So I'll show where we can get the same cloud, water, and precipitation with the microphysics running from 10 seconds to 300-second time steps. This is totally messed up when you start coupling it to things like club and the deep convection. So it doesn't give the full physics package time step stability, but it does, at least we know the microphysics can give us that stability. And then we tweaked it a little bit. We allow accretion to see the auto-converted rain. We thought this might help reduce the indirect effect. It doesn't, but we're turning it on anyway. Some other things that are nearly ready a refactored autoconversion and accretion that I'll talk about, which is using machine learning for warm rain, which I think gives a whole bunch of solutions. I don't know if it's gonna be ready for CAM 7, we'll see. So this is just the time step stability. Laser in here? No. Where is it? Pointer options. Anyway. Pointer's fine. Okay. What this shows, the red is pumas. This is for a MPACE case, and it's a bunch of different species: liquid, ice, supercooled liquid, rain, snow, and cloud fraction. And what the different lines, which some of them overlap, are going from, as I said, 300 seconds down to 10 seconds, where we're substepping the microphysics within one club substep in a time step. So everything else in the model is the same except for the microphysics subcycling, and it's giving us the same solutions you'll see in red at 10 seconds or 300 seconds if we use 30 microphysics substeps or just one. That's actually really nice. You can see in the older version, the blue, we don't actually get that, particularly for cloud, liquid, and precipitation. And this one in the middle is a test where we just take all the changes and back out the sedimentation changes and go back to explicit sedimentation, and that basically gives us more spread again. So what it shows is the implicit sedimentation is giving us the stability. Traditionally, this is slightly diffusive, but in these climate simulations and for rain, it's not really important. This time step stability, I think, is more important. So one of the other big ones is this change to the NI max. So there was an artificial limiter on ice number, and what happened was it suppresses CAM6 ice nucleation when the Myers ice nucleation was removed. So in CESM, this was also there, but it wasn't really affecting the simulation because we were using the Myers ice nucleation, which was getting added to this limiter. When we took it out and we put in the classical nucleation theory for CAM6, that didn't get replaced. And so it results in less ice and more supercooled liquid water in cold climates in CAM6. This was not intended. It's a feature of the simulation. Would you call it a bug? Well, it's an artificial limiter on ice nucleation. It's not necessarily wrong, it just wasn't intended. So this was noted by Zachary McGraw at the University of Oslo and Columbia, and also Trudy Stalermo. We made these changes in a version that was picked up by Zhang Zhu to reduce the paleoclimate sensitivity, but there were some other time stepping things involved in that, so that's not really the solution we decided to go with. What happens is if you remove this limiter on the ice nucleation and put the classical nucleation theory in here with no limiter, with immersion freezing, you get incredibly large ice numbers. So the base ice number is on the order of 40 to 50 per liter, which is about what David Mitchell was showing yesterday from observations. This increases it by a factor of 10, and it's due to dust, which is why you see it in the cold end of the range right before you hit the homogeneous freezing limit over essentially desert regions of the subtropics in the northern hemisphere. Small amount of dust getting lofted up there in the upper troposphere creates a huge number of ice nuclei. So what we've done for CAM7 is a couple of changes after talking to Simona and to Zachary. So there is a switch that we can throw in the ice nucleation that gives a better calculation and a more consistent calculation of aerosol number for ice nucleation. That gets us about a third of the way or halfway there. And we set that to false. We actually do a calculation then based on the actual modes instead of using a parameterization for ice number, which we should not be using for dust. And then we've also, because there's a limit on BC for the ice fraction in the immersion freezing, we're also putting one on dust of 5%, and that gives us this. We still see the impact a little bit, and you'll notice the scale is a factor of 10. So we're getting some 20 to 30%, 50% increases in ice number here due to immersion freezing, which actually I think is real, but we're keeping that at some moderate level so it doesn't really affect the climate. So we've done a bunch of global tests. Basically, these are sort of standard 6-year F2000 CLIMO tests, present day, pre-industrial SSD4K. There's not much change in the cloud feedback, doesn't really alter the climate sensitivity. Puma's code reduces the liquid water path and the ice water path for control. This does not have all the new club changes that are going in, so that will affect the liquid water path and the ice water path again. But the red line shows that we can bring back ice to something a little more reasonable, larger, and actually get the top of the atmosphere fluxes back in balance again. So I just did this simulation to show that it's imminently tunable when we actually get to the assembly of the final model. There's not much change in net aerosol cloud interactions, but we are reducing the magnitude of the components of the shortwave and long wave, which is good. And the percent change in liquid water path, and here's another way, is also lower, and the drop number change in all the PUMA's configurations is significantly lower than the control in the Northern Hemisphere. So this is actually moderating some of the indirect effects. And we actually do see with this tuned version with more ice, the stronger ice clouds, we are getting fairly significant reductions of 30 to 40% in the ACI, so I think there is potential here for that in CAM7. Then this is coming attractions. This is a paper, you've seen me talk about this before. This is last year. Basically what we just asked is, can we do the warm rain process better with machine learning? So what we did is we replaced the traditional bulk rain formulation with the rain formation process from a bin model, the stochastic collection equation. We take the modes, 2 modes for liquid and rain, and we discretize them into the 32 bins of a bin model, and we throw that into the stochastic collection equation. We calculate the change in each bin, then we compose it back into modes, and we calculate the difference in the modes as a tendency, and we constrain all that to be mass conserving, and we can put that into the model. I'll show you it produces great results. It also slows down the entire code by a factor of 5. It's totally impractical to run operationally. But we then go, thanks to David John Gagne and his team, we built a machine learning emulator of that. And what this shows is just that the bulk and the bin scheme give you very different tendencies for the rain tendency, which is essentially the combination of autoconversion and accretion. You're getting quite different values. But when we emulate it, this is the bin solution here and the emulator, you can see we're getting a really good representation of that reconstruction. We've actually run this in the model, and what's really nice, this is what I think is really interesting, it gives us some really nice higher order statistics of rain and gets rid of some of the long-standing biases in the GCM. So what this panel these panels show is this is the rain rate in the colors, so this is high rain rates as a function of liquid water path and effective radius. And what you can see is that at any effective radius, as you go to higher liquid water paths, you just start forming rain. That's the feature of the Karutinoff and Kogan simple version of a multivariate linear regression, which has autoconversion at all drop numbers and any liquid water path, and it's nonlinear. What actually happens, however, is in physical terms, you don't get rain in a bin scheme unless you get particles of something like 14 to 15 microns. It's just not observed. And a bin scheme does that. So what you see when we run the bin scheme is even at high liquid water paths, there's not much rain rate. It's much lower. And we see this real sudden onset of rain at any liquid water path at 15 microns. The other way to do this in a bulk scheme, what most GCMs with a bulk scheme do, is they put in a size threshold. They don't turn on the autoconversion until 15 microns. But that's only empirical. So what's nice is this is the GCM producing this result fully physically, except it's too expensive. However, if we emulate it, we get the same result. The other thing that happens is because it's not raining all the time, the frequency of occurrence of precipitation, the persistent dreary drizzle problem in the GCM, in the subtropics in particular, here's the control model. This is frequency of precipitation, and the purple line is CloudSat. This goes away for large-scale precipitation. The convective scheme's still messing it up, but we're not going to talk about that. But you can see this produces some really nice things and gets rid of some really long-standing biases and doesn't really impact other aspects of the climate like ACI or cloud feedback. So Cheryl is helping us with David John Gagne, and through the LEAP project, we're trying to get this into the final version of microphysics and train the emulator again and have a pathway that we can train the emulator in the final version of the code and actually get this into an operational level in CAM. So a couple more next steps, more testing at high resolution. Bill Skamrock talked about this yesterday. We're pushing this at 3 kilometers. We're analyzing the PPE in a number of different ways that Truda talked about. We also are working on a joint PPE with some other institutions, NASA, GEOS, GIS, and we're probably going to add E3SM to that since I know people over there now. And then there's the refactored autoconversion and accretion that we're going to try to get in there with LEAP. Next things that are coming, this is nowhere near Chem 7, so don't have a heart attack, Julio. it's fine. This will be beyond that. We're gonna evolve this into something that's P3-like, where we unify the ice and snow. That's been done before, but we're trying to do it in a more robust way. We're incorporating, and then other plans, or we might even try a single category liquid. At the minimum, we're gonna put a more flexible structure for the liquid size distributions, which is coming from other ongoing work that Hugh's done. So part of this is moving this into a framework where we may actually switch the whole thing over to P3 once we get to P3-like. It's not a big lift to turn Pumas into a P3-like scheme. And then if we want to actually just replace it with P3, it would be relatively straightforward conceptually. Again, we're talking about a couple of years down the road. Software engineering, actually the pack and pack's already gone. And the CCPP metadata ports, I'm committed to help do that as soon as we actually get to that process. So Jesse and co, I'm happy to help with that. So lots of updates in microphysics. The big one is this NI-max change and then the emergent freezing adjustments. Implicit fall speed and sedimentation improves things. The machine learning's coming. That's the other thing to look at. And there's not much impact of this. An emerging thing, if people have been following the thread, is there's another issue with the substeps and some of the cloud-borne aerosols that we're going to end up fixing, which is work that Adam's engaged in, I'm engaged in, as well as Chuck and Simona and ACOM. But that's hot off the press and filling up our email boxes as we speak. That's it.
Maybe one or two quick questions?
So, with respect to the your emulator, and you do a stochastic collection, you then put it into the modes, the standard modes for MG2, is that right?
Yeah.
So how dependent on that is that if you, for example, change some of the tuning, how would you have to redo the actual machine learned part of the emulator?
That's a good question. We found it was pretty stable when we used it. I think because we're training it at every single point on the planet with the microphysics, retuning the model is not going to be a problem. Vastly changing the microphysics might involve in some, but because we're limiting it to this one process, you can think of it as literally a drop-in process replacement. And we actually are building it, Cheryl's got it coded as a name list option that you basically, it's a micro MG warm rain, and you can say KK2000 tau or emulated. So it's just a drop-in process replacement, and because all the processes are bounded by mass and energy conservation at about 2 different levels in the microphysics, individually and then all together, it's highly likely we're gonna blow anything up doing this. We are also exploring, like, what happens if you take the same emulator trained in one model and put it in a different model, which is essentially what we do now with KK, because it was trained in LES and we put it in a GCM. Right. We don't know if that's gonna work. So that's another interesting aspect. So it's still early days. I'm not proposing we jump forward into this. We're gonna try to make it work and start testing it. We're trying to get the framework in there so it's plug and play, and if you want to turn it on, you just flip a switch. You don't have to go talk to a bunch of people about it. Good question.
Okay, so.
The time step stability results, was that the 58 or the 32 level model, and does that matter?
It is a 32 level model. I hope it doesn't matter for the microphysics because, again, I'm holding club constant, right? So we know that club is more sensitive. It might be more sensitive well, I wouldn't think because it's implicit that the vertical level structure is gonna matter if it's finer, because that wide range of time steps, we're crossing a huge Courant number space, which is why we have the implicit scheme in there to kind of get around that. The other thing is this does speed it up because we're not looping over, we're not sub-stepping for the sedimentation. The microphysics is 10% faster when we do this. So it doesn't hurt, it's like 1% model runtime or something.
Those different colors, they don't seem
The
to
different colors are
converge.
different types of code, the different thicknesses and line styles are different time steps.
But they do not converge to the same solution when the time steps are very short.
Well, the 3 different ones are not going to converge to the same solution as 3 different microphysics codes.
Oh.
Right, so blue is MG2 and red is Pumas and the orange is intermediate. What you would want to see is each of the colors converge. So the red, you can only see one line. That means it's pretty much converged. In the orange, you can see lots of lines, same in the blue.
that means it's not converged with respect to time step.
Okay, so maybe let's move on to the next presentation by Isaac Davis, who will talk about different cloud regimes in the model and in satellite data. Do you see it from online? Okay, good.
Thank you. Can you hear me? The mic. Okay. So my talk is called Cloud Regimes in ISCIP, Modis, Miser, and CAM. And for those of you who aren't familiar, ISCIP, Modis, and Miser are three different cloud satellite data products. And they measure cloud in histograms that look a bit like this. This is a random example from ISCIP. So we have on the x-axis increasing cloud optical depth, and on the y-axis decreasing cloud top pressure. And then the color of each bin is the percent cloud cover measured in that bin. So for example, this bin up here has, it's very thin cloud and it's very high in the atmosphere. And this bin down here is very thick, very low cloud. And we can take these histograms and make something called cloud regimes out of them. And we basically do that by flattening the histograms down, in ISCIP's case, into a 42-dimensional vector. So we flatten them all down and we can feed them into k-means clustering algorithm. And basically k-means is a clustering algorithm. It's one of the simplest and most popular unsupervised machine learning algorithms, and it just seeks to create cluster centers of data that is very compact within that cluster, and each cluster is hopefully very different from each other. So these cluster centers that it outputs are our cloud regimes, and you can see them on the right there. So here, again, are the cloud regimes. These are the histograms of cloud, and then on the right, we see their spatial distributions. So we can see cloud regime 1 is very thin, high cloud, and it occurs mostly over land. We do have we think that there might be some erroneous retrievals in this cloud regime from ISCIP, especially over high altitude and ice. Cloud regime 2 is also high cloud, mostly over land, but more in the north. Cloud regime 3 is much lower, thicker cloud, and it hangs out off the west coast of North America, South America, Africa, and Australia, and this is kind of our stratocumulus regime. Cloud regime 4, again, high thin cloud, except this one seems to be associated with tropical deep convection. You can see it mostly in the ITCZ here. Cloud regime 5 is kind of mid-optical depth, mid-altitude, and seems to be associated with mid-latitude storm tracks, as you see here. Cloud regime 6 is just kind of a catch-all for shallow convection, and cloud regime 7 is just low, thin cloud over the ocean. So I just wanted to throw this up real quick. I'll only have time to really talk about the ISCIP results, but we do everything in this presentation for both MODIS and MISER. So here are the results for MODIS on the left and MISER on the right. And these two, we only found 6 cloud regimes for. We have a whole process that we go through to decide how many cloud regimes to make for each data product that I won't get into here. So after we make the cloud regimes for the satellite products, we can then apply model output to them. And we do this using a package called COSP, which runs in line with CAM and produces histograms that are very comparable to the ISCIP, MODIS, and MISER ones, and sort of emulates if they were observing our simulated Earth, what would they see? So then we can fit those model histograms into our satellite cloud regimes. So that's what we have here. On the left are the ISCIP cloud regimes, and on the right are the ISCIP cloud regimes, but as reproduced by CESM in the ISCIP simulator from COSP. So overall, CESM does fairly well recreating the distribution of cloud regimes, but it does have some biases, of course. Namely, it underrepresents the frequency of occurrence of high, thin cloud. As you can see in cloud regimes 1 and 2, both of these are underrepresented in CESM. It also overrepresents cloud regime 5, our mid-latitude storm track related one, by a good amount. And we do think that some of cloud regime 2 might be getting clustered into this one. So maybe in the model, it doesn't distinguish between that high thin cloud of cloud regime 2 and the somewhat lower thicker cloud of cloud regime 5 as well. So they're getting mixed together into cloud regime 5 in the model. But other than these two biases, CSM does very well. As you can see, cloud regime 3 looks very similar between the two. Cloud regime 4 looks excellent. Cloud regime 6 looks pretty good. It's slightly denser over land in the model than it is in ISCIP, but it still looks very good. Cloud regime 7, it occurs in all the right places, but it is slightly underrepresented. So this obviously provides a pretty powerful tool for evaluating clouds in the historical simulation. But there's no reason to stop there, and we can apply this to future warming simulations, which we do by use of the SSPs. So we also apply the cloud regimes to SSP 1, 2, 3, and 5. And here are some time series of their frequency of occurrence, where the blue line is the historical simulation, and it branches out into the colored lines, which are the frequencies of occurrence in the SSPs. So a thing to note here is that we do see a reorganization of the regimes as the climate warms, and it does matter how much the climate warms, it responds to those. Some cloud regimes become more prominent and some decrease in frequency of occurrence. We also see in this top left plot that the total percent cloud cover decreases in all SSPs. We can take a slightly deeper look into this by taking a look at this plot on the right, which shows the frequency of occurrence of each cloud regime in SSP3 from 2071 to 2100, minus the frequency of occurrence in the historical simulation. And SSP3 is sort of thought to be the most plausible climate outcome of the SSPs, which is why we chose it. And things to note here are in cloud regime 3, our stratocumulus regime, we see these stratocumulus cloud decks kind of thinning out, and cloud regime 3 becoming less prominent in those areas. We also see cloud regime 5, kind of our mid-latitude storm track one, becoming much less prominent above 30 south and decreasing overall. And cloud regime 7 also sort of fades away and is just blanket kind of disappearing. And most of these differences are made up by an increase in cloud regime 6. And this is important because of these cloud regimes' cloud radiative effects. Here we have violin plots of the cloud radiative effect for each cloud regime. And you can see on the left, cloud regime 3, 5, and 7 all have the strongest radiative effects. The blue violins are for the historical simulation, and then the lines and dots represent the medians and interquartile ranges of the SSP's forcings. So these ones that we all saw decreasing in frequency of occurrence have the strongest radiative effects, and it's being made up by cloud regime 6, which is appearing in their place. So this is indicative of a strong positive cloud feedback that's been observed in CESM previously. We can look into this a little bit deeper by breaking down the frequency of occurrence of the cloud regimes in terms of dynamical regime, so in terms of the large-scale vertical velocity that they occur in. So on these plots to the left, the x-axis is bins of omega 500, and as you move to the left, these regimes are more convective, there's more upwelling air. On the right, it's more downwelling air, more subsidence regimes. So this plot is for the ISCIP observation, and then CESM historical. And we see that, again, CSM does pretty well representing the distribution, but with the same biases we saw earlier, being a little underrepresented thin high cloud and overrepresented cloud regime 5. And then over on the right, we have the change from SSP3, again from 2071 to 2100, minus the historical simulation. So the outline of this plot kind of outlines the change in PDF of the omega 500 distribution from the historical simulation to SSP3. And in this plot, we see a decrease in subsidence regimes in general and a shift towards weaker subsidence and shallow convection. And most of this disappearance in the subsidence regimes is made up of cloud regimes 3, 5, and 7. And most of the increase in the weak convection, weak subsidence is made up by cloud regime 6, which again was our weak convection regime. So this kind of gives us a framework to evaluate these changes based on large-scale circulation. So in conclusion, we've applied the concept of cloud regimes to 3 different cloud data sets. And then we apply those same cloud regimes to CESM output. And CESM did well overall, putting the cloud regimes in the right places, but did, of course, have some biases. And then we applied the cloud regimes to SSP simulations to investigate how cloud structures might change with a warming environment. And then diagnostic approaches like the Omega 500 breakdown let us understand the changes in terms of their driving physical factors. So that's all I have for now. Are there any questions?
Questions? I have a very quick question. How easy would it be to plug off some of your plot into the ADF? Yeah.
It's possible.
I think I
the
don't know to compare like if we have the output, of course, but I feel that it's really nice. I feel the plot that you have shown where you see the one where you see the comparison. This one. Would it be easy to plug? Maybe this is something.
I'm not.
You haven't run. But
easy in the sense that it would, getting Isaac scripts put into an ADF-like framework would be easy. The downside would be that we'd have to do the k-means clustering. Oh no, we could save the observed clusters. Yeah, it would be actually pretty easy and it wouldn't be much of a penalty once we have the final clusters to do.
And it would be good to know which output, if we can run by default.
You have to cost one.
Yeah, the cost one by default, but is it going to give me a lot of output or just the one that, if there is something specific, maybe we can solve this after.
That we can fine tune, no problem.
Yeah.
But it should be
Yeah.
so that's not so bad.
No, I just wanted to ask about some of the regimes in ISKIP over land have a lot of detail, and you seem to imply that you might not trust them.
We don't have enough proof to dismiss them, but a little skeptical.
Okay.
When you do the k-means clustering, you need to specify the number of clusters in the beginning, right? And the reason you have like 6 major clusters, is that because of the number of k that you use, or how sensitive is your result?
Yeah, so we do need to specify k, and we have a large process that we go through beforehand. We do the clustering for a number of different values of k and do some evaluation to choose which produces like clusters that don't overlap with each other the most, but also capture all of the different cloud regimes that might be there. So we do a lot of analysis for that.
Yeah, just one quick question, because I don't know enough about COSP. Is this something that, in addition to like the ADF, you could do with another CMIP class model or something? I mean, do you have to be like cognizant of doing this when you run the model, or is it something that could be done with post-process data?
COSP needs to be run at the same time the model is run, but then after that, you can do it with any model. I think it doesn't matter, that's CSM, anything.
Okay. Yeah, it's a very interesting process-oriented type diagnostic, and given the community motivation for that, I could see something like this being useful there too.
E3SM, for example, you can turn COSP on and you have the output, and probably one can.
Almost everybody has cost.
Right, so nowadays.
And most of them have some simulations with CMIP6 with cost on monthly mean. So you could get these histograms out of some of the RFMIP simulations, for example, that are in the archive.
Yeah, one detail that Isaac didn't mention is that we're using the monthly means here, and that the idea behind that was that most of the models only produce monthly mean outputs, so that would be what you would do for a multi-model comparison.
Okay, cool.
Yeah, our next presenter is online. Ling will talk about convective cloud microphysics. Ling, are you able to share your screen and control your slides?
I'm not sure. Seems I cannot share my screen. Let me see.
Can you try again?
Yeah, I'm trying. Sorry, I have to exit and relog.
We also have a presentation. We could control it from here.
She's in companion mode.
Okay.
She's not there. Oh.
We could hear her, so we could advance the slides for her. Oh, is it possible for you to test do something with her, aside, and then while we move on to the next talk, and then let her present that?
Is that okay with you guys? Do you want to do that?
Yeah, I guess.
She's
Oh,
there.
she's ready?
But
She cannot share her slide.
Well, no, do we have, she shared her screen.
She shared?
She just did it the wrong way. There she
Oh,
goes.
okay.
can you see my screen all right now?
I can see your screen, but not your.
Oh, cool. I see. Is everything all right?
Okay,
You can
yeah.
hear me and see my screen all right?
Okay, looks good. Take
Cool.
it.
Cool. Hello everyone. My name is Ling Ming, and I'm a graduate student working with Professor Hong Liu at Texas A&M University. And thank you very much for the opportunity. And I'm so excited to present you the climate impacts of connective cloud microphysics in the NCAR-CAM model. In this slide, I also acknowledge my collaborators and the funding agency. So a quick motivation and objective. In global climate models that are usually characterized by roughly 100 kilometers in the horizontal resolution, the kinetic clouds need to be parameterized due to the cost model resolution. However, the kinetic microphysical processes are usually oversimplified or even neglected. So in the schematic diagram I show you in the left, complex and interactive microphysical processes occur within cloud, including deep convective clouds. So such oversimplification hampers our ability to faithfully represent convective clouds in global climate models. A handful of convective cloud microphysics schemes emerge to kind of address the issue. However, one general issue is that the existing kinetic cloud microphysical schemes are developed mostly based on the stratiform cloud microphysics scheme. That implies if the cloud parameterizations are cloud type aware, that means if we directly use the cloud microphysical parameterizations of stratiform cloud for kinetic cloud, that might be problematic. So the objective of this study is to evaluate and improve the kinetic cloud microphysics scheme for global climate models, including the CESM CAM model. So this slide shows you a schematic diagram of a double moment forecast cloud microphysics scheme developed for convective clouds. So the processes in black, the default scheme developed by Song and Zhang 2011. Those in blue are the processes that we modify or are newly added to the default scheme. So I just highlight a few aspects that are of interest. First of all, cloud ice particle. In the default scheme, cloud ice particle is assumed to suspend in air. In our new scheme now, we parameterize the cloud ice to sediment based on the Davis and Reynolds number parameterization as a function of ice and airflow properties. For snow particles, now we replace the original snow terminal velocity with a more physically based terminal velocity parameterization as a function of isotope content, pressure, and temperature. The original snow terminal velocity is parameterized as the terminal velocity and diameter parallel relationship, and that's for stratiform clouds. So this motivates us to use a more convection-oriented parameterization for the snow terminal velocity. And second, we enable kinetic snow to detrain and fit the large-scale cloud scheme. In addition, we also add a new grapple category. Now we make the original 4-class scheme to become now a 5-class scheme, and we add a set of grapple microphysics. And because deep convection usually provide a more favorable environment for generating the rime ice particles, so we believe adding a new grapple category is more appropriate for the cloud microphysics for kinetic clouds. And finally, we modify the cloud, the warm rain formation processes in the convective cloud constrained by satellite estimates. For more technical details on these modifications, please refer to our 2021 and 2023 paper. Then we set up a bunch of experiments to account for the impact of the incremental modifications we make to the convective microscheme. So first, we conduct the ZM experiment. That's the default CAM 5.3 model. The convection processes are just described by the Zhang McFarlane or the ZM convection scheme. And this scheme has oversimplified cloud microphysics for the convective cloud. And second, we conduct the SD experiment. And in this experiment, we turn on the Song and Zhang 2011 convective microscheme on top of that's embedded in the ZM scheme. And third, same as the second experiment, now we calibrate the coefficient in the parameterizations of warm rain initiation and generation processes. And for the fourth experiment, same as the third experiment, now we use the Davis and Reynolds number parameterization for the cloud ice terminal velocity, and the Althusser et al. 2017 or EL17 parameterization for the kinetic snow terminal velocity. For the fifth experiment, same as the fourth experiment, now we add a set of grapple microphysics and the rhyming processes. And then finally, we enable convective snow detrainment in our sixth experiment. Now let's look at some results. Compared to the satellite synergy liquid water path climatology, like I show you in panel A and B, we find that the SD experiment, like I show you in panel C, produces way too much liquid, especially over the tropics. And in the lower left, we decompose the total liquid content into the stratiform and the convective component, and we find that the large amount of liquid content over the tropics contributed solely by the convective liquid content. And the excessive liquid in the tropics results in the substantially underestimated net top of atmosphere or TOA solar fluxes. Like I show you in the table in the lower right, compared to a series above, the net top of atmosphere solar flux simulated by the XZ experiment is about 15 watt per square meter off compared to a series above. And then we speculate that the warm rain processes, like the warm rain initiation and the formation processes within the default convective microphysics might be too weak. That caused the model hold so much liquid in the atmosphere. So because the default convective microphysics use the famous KK2000 parameterization for the autoconversion and accretion process rate. So the KK2000 parameterization actually were developed for the marine timeshare, the cumulus cloud, and failed to reflect the fast autoconversion and accretion rates in deep convective cloud. So as a first attempt to address the large amount of liquid content over the tropics, we now enhance the autoconversion and the accretion rate, like I show in panel B in both left-hand side and right-hand side, guided by the satellite estimates of the cloud liquid path climatology and the series above TOA radiation budget. So now we enhance the auto-conversion and accretion rate when compared to the original KK2000, like I showed you in panel A on both sides. When we calibrate, after we calibrate the warm rain production in the scheme, we see consistent improvement across the liquid content, liquid path, and TOA radiation budget and the cloud forcing. So now the liquid path simulated by the SD after tuning experiment over the tropics looks more reasonable and in much agreement with their liquid path climatology estimate. And for the TOA solar radiation budget, the value simulated by the SD after tuning is much closer to the series EBOF estimate. And on the right hand side, I show you the shortwave cloud forcing and the longwave cloud forcing, and I would like pay attention to the shortwave cloud forcing and compare to the default convective microphysics that's in gray line here. The too strong cloud shortwave radiative forcing due primarily to the excessive convective liquid over the tropics is largely ameliorated now over the tropics and latitudes in better agreement with the series EBOF estimate. So in addition to the liquid content, we also look into the ice water content. This slide shows you the convective ice water content profiles over a number of convection hotspot regions over the globe, and we compare the results against satellite estimates. So compared to observation in the black dot line, the SD and SD after tuning experiment overestimate the ice water content by a factor of 2 to 4 consistently. And the overestimation of the convective ice mass is alleviated with the improved ice microphysics. And we find the most important process is adding grapple microphysics and the resulting increase in the hydrometer fall speed in reducing the overestimation of ice water content, as shown in the blue line. And finally, we discuss a bit on the frequency of heavy and light precipitation. So this figure shows you the frequency of total convective and large-scale precipitation rate, and we compare the result with their trim and estimate. So the ZM experiment exhibit a common bias of too much light precipitation and too little heavy precipitation. But when we turn on the convective microphysics, some heavy precipitation events are reproduced. And the PDF of the rainfall rate is quite sensitive to the warm rain processes in convective clouds. So when we enhance the warm rain production, we shift the PDF toward heavier precipitation, which agrees better with the trim estimate. And most of this increase in the heavy precipitation event comes from the increase in the convection precipitation. So the common bias of overestimating light precipitation and underestimating heavy precipitation frequency are mitigated to some extent. And you may already notice that the heavy precipitation events are less sensitive to the ice microphysics, and there are a number of possible reasons for this. First, the precipitating hydrometers like snow and graupels already dominate the ice phase condensate. On the other hand, the suspending cloud liquid, the mass of suspending cloud liquid and the precipitating liquid are quite comparable. So if we convert more suspending liquid to the precipitating mode, we can produce more heavy precipitation. However, this is not the case for the ice phase condensate because snow graupel already dominate the ice phase condensate. And second, numerical integration limitation. Now we integrate the precipitating hydrometer budget equation from bottom to top along the updraft. That means the condensate falling from above is not accounted for due to numerical difficulties. So the current numerical framework limit the impact of the changes in the ice microphysics. And finally, a quick summary. we improved the achievement of connective cloud microphysics in the NCAR model by first implementing new terminal velocity parameterizations for convective ice and snow particles. Second, adding a set of grapple microphysics. And third, considering conventional detrainment. And finally, enhancing rain initiation and generation rate in warm clouds constrained by satellite estimate. And the cloud shortwave radiated forcing now is much improved over both the tropics and mid latitudes when warm rain formation is constrained by liquid path climatology, theory radiation budget, and the cloud forcing observations. And third, overestimation of convective ice water content is ameliorated by improving the convective ice microphysics. And among most of the processes that we modify, adding grapple microphysics and the accompanying increase in hydrometer fall speed is the most important process. And finally, the common bias of more light precipitation but less heavy precipitation is alleviated. And for more detail, please refer to our two publications that are associated with this study. And thank you very much for your attention. I'm happy to take any questions you may have.
Thank you, Lily. Maybe one quick question from the audience here. Is there any question from online? No. Okay, so then thank you again, Lily. We will move on to the next talk.
Thank you.
Thank you. Margaret will talk about parametric sensitivity of cloud feedbacks in CAM 6.
Can you hear me? Okay, great. Hi, everyone. So I'm going to talk about cloud feedbacks now in CAM6 and the sensitivity to parameters using the PPE that Truda described in her talk this morning. Okay, so I'm Margaret Duffy, and I'm a postdoc here at NCAR and CGD, and I've been here for a little over a year. Okay, so the motivation for studying cloud feedbacks is climate sensitivity, which is a very important quantity because it measures the degree of warming per doubling of atmospheric CO2 concentrations. But it's also a very uncertain quantity, and we can see from this figure that we started trying to estimate ECS in 1979 with the Charney report with an estimate of 1.5 to 4.5 Kelvin of warming, and that it's been very, very difficult. Whereas we're moving to the right, we're moving through time of assessment. It's been very, very hard to constrain, even though it's such an important quantity. And this is the just equation showing how this important quantity ECS is related to cloud to feedbacks, and cloud feedbacks in particular. There's an inverse relationship between the ECS in Kelvin and the feedback lambda, which can be separated into its cloud and non-cloud components. Okay, so most of the uncertainty in the feedback lambda is shown on the right here. Looking at the spread around these colorful dots, we can see that most of that spread is coming from the cloud feedback in this column second from right, and that's robust across these different assessments. So each color is a different assessment. Okay, so now let's move into model world and talk about what models are saying about ECS. So starting over here on the left, we can see that the spread in ECS has actually increased from CMIP 5 to CMIP 6. So the CMIP 5 models are in blue, the CMIP 6 models are in orange, and that when we break this down into the forcing and the feedbacks on the right, the total feedback is over here and the cloud feedback is over here, that a lot of the spread across both CMIP 5 and CMIP 6 models is coming from cloud feedbacks. This is a familiar figure, some of you may have seen this before, but I've added stars indicating where the NCAR models fall. So NCAR had 2 contributions to CMIP 5 and 1 to CMIP 6. And we can see that as we progress through time from CCSM 4 to CESM 1 to CESM 2, the ECS has increased over the model generations from something like 3 to over 5 Kelvin. Okay, so I'm going to be talking about the role of parameters on the cloud feedbacks, which are so important in this ECS. Here's a schematic of the parameterized processes in atmosphere in an atmospheric model, in our atmospheric model. And I've just highlighted the areas where the parameters that I'm studying fall. This should say MG2. You're probably the only audience who even knows what that means. Sorry about that. But we're looking at sensitivity to parameters in convection, aerosol, turbulence, and microphysics schemes. And these are 45 different parameters. Okay, so this is the same PPE that Truda introduced this morning. It's the CAM6 atmosphere only, CAM6 atmosphere model. 45 parameters are being varied across 262 simulations. They're 3 years each with fixed SST, and I'm going to be focusing on 2 experiments, the present day and the SST 4K. And the difference between those two is the feedback that I'm talking about. Okay, so this is an old version of the slides, I'm sorry. Okay, that's okay. What I did, though, was subset the simulations for my analysis from 262 to 206 using top of atmosphere radiative imbalance. So even though the 45 different parameter values are intended to have realistic values, the different combinations of the different parameter values you can imagine wouldn't necessarily always yield a realistic looking climate. And so to deal with the potential that some of these 262 simulations might look funky, I have subset them based on top of atmosphere radiative imbalance. So I'm only keeping simulations which have a TOA radiative imbalance within 15 watt per meter squared of the default for both the control and the 4K simulations. Okay, so now let's actually look at the cloud feedbacks in this ensemble in the PPE, and we can compare it to the CMIP6 model. So the CMIP6 model spread in the cloud feedback is shown in green, and the PPE spread in the cloud feedback is shown in purple. And the total feedback, cloud and non-cloud, is shown also here on the left. And we can see that there's very comparable spread in the feedbacks between the PPE and the CMIP6 model. So that means just by changing parameters, we've been able to reproduce both the parametric and structural differences across the CMIP6 models. And so I want to know, is this the right answer? Is it for the wrong reasons or the right reasons? And so, you know, is this a coincidence that these spreads are comparable, or is there, are the mechanisms that are setting them the same across the two ensembles? And so the first way that I look at this is I decompose this cloud feedback into its shortwave and longwave contributions, and we can see that we continue to see similar spreads across the PPE and the CMIP6 models, even with this decomposition. And then I'm going to do one more decomposition now into of the total cloud feedback into 6 mechanisms. And so these 6 mechanisms come from the Sherwood report, which some of you have probably read. And basically these are 6 kind of known processes that affect the cloud feedback, and they have this assessed value that's based on multiple lines of evidence. So this is a figure from the Sherwood paper. This is showing the 6 different cloud feedbacks that I'm going to be decomposing our total cloud feedback into, and what their assessed mean and spreads are. So if we do this for the PPE in blue, we can compare to I've now switched from CMIP to AMIP, it doesn't really make a difference, to the AMIP models, and also compared to the assessed value in orange. So the total feedback is shown here on the bottom. Our PPE has a higher mean total cloud feedback than the CMIP models and the assessed mean value, but the spread is very, very similar, and the spread across our 6 individual mechanisms is also quite comparable between the PPE and the AMIP models. So there's a lot on this slide, and since I'm focusing on spread, I've just in numbers put what the 1 sigma ranges are in watt per meter squared per Kelvin on the slide so that you can easily compare the numbers that for the point that I'm trying to make, which is that the spreads across each process are very similar. So the question that I was trying to get at here was, are we getting the same answer for the same reasons or the same answer for different reasons? And I would say, by and large, we're getting the same answer for the same reasons. The processes setting the spread in the CMIP models are very similar to the processes setting the spread across the PPE. Of course, we have an advantage using the PPE as compared to the CMIP models, which is that we can actually look at what parameters are changing from ensemble member to ensemble member. You can't necessarily do that so easily in the CMIP models. And so what we can do is we can just look at which parameters are most highly correlated with the total cloud feedback. So remember, there were 45 parameters. I'm showing you the 3 most highly correlated parameters on the slide. And there is one parameter from the microphysics scheme, one from the convection scheme, and one from the turbulence scheme that are most highly correlated with the cloud feedbacks. You can see, looking at these scatter plots, I have the parameter value on the x-axis and the total cloud feedback on the y-axis. You can see that there's a lot of spread even for this most highly correlated parameter, the ice-snow auto-conversion threshold. There's still quite a bit of scatter, and I think that that's telling us that there's just more than one parameter, right, affecting the total cloud feedback. It's a combination of a lot of parameters that are setting that spread. Okay, finally, I introduced that we saw an increase in ECS from the CMIP5 models to the CMIP6 models in our NCAR contribution. So I wanted to know, given that it's clear that we have so much sensitivity to parameters, is that the reason why we saw that big increase? And so I'm going to address this question using just a very simple regression model. This is using a lasso regression with our predictor is the total cloud feedback, 206 of them, 1 per PPE simulation. And then our kind of our Ys, our response is our cloud feedback. Our predictors, our Ys, are the parameter values, the 45 different parameter values. Again, 206, 1 for each simulation that I'm using here. And what I can do then, once I've built this model, is plug in the CAM5 values for my P's and plug in the CAM6 values for my P's and see whether I get a different estimated total cloud feedback. I've done just exactly that here on this slide. Let me walk you through it. The total cloud feedback spread is shown in purple here on the right, and our regression estimate is shown here second from right. And then the estimate using CAM5 values plugged into our simple model is the blue star, and our estimate using CAM6 values plugged into the simple model is the orange star. And this is telling us no, changes in parameters are not responsible for the change in cloud feedback. It's something structural with the model. So even though we have this very large sensitivity to parameters, that's not what's responsible for the change from CAM5 to CAM6. Okay, so I've posed 3 questions, and I think hopefully taken a stab at answering them over the course of this talk. We saw that the spread in the total cloud feedback was the same or very similar between CAM5 and, between the PPE and the CMIP6 models, and I asked whether or not that was a coincidence, and I think it's not, based on the fact that the processes setting that spread are very similar across the 2 ensembles. Then I asked which parameters were important, and I showed you the influence of 3, a microphysics, convection, and a turbulence parameter. And then I asked, given this very large sensitivity of cloud feedbacks to parameter values, is that what changed and increased our ECS? And my answer was no. So again, my name is Margaret Duffy. My email is here on the slide. I also sit here in the MESA lab. Thank you.
Not immediate questions. Is there anything from online? No. Okay. So then, thank you again, Margaret. Let's move to the last presentation of the cloud block. We will have an online presenter again, Mengxi Wu. Mengxi, could you try sharing your slides? Mengxi, you are muted, I think.
Sorry, it seems I can show my screen. Would you mind open my slide which I uploaded this morning?
Okay, you can see it in this folder. Let's see whether we can find your. This one.
That's it.
This one, yeah.
You have to download it.
Okay. So can you download?
It should already,
Oh, it's
everything,
already?
yeah, everything today has already been downloaded.
That's the next one, that's the next
One
one.
above it, right?
So
This is the
maybe
one that
it's
hasn't been
downloaded
downloaded.
somewhere else. So we need 8.
So you put it in late,
Okay, yeah, okay, so can you download?
important lesson on getting
So he doesn't
things
get
in
it
on time.
Thank you. Thank you.
So, Maxi, so when you want me to move to the next slide, please say next slide, I will control it for you.
Okay, thank you so much. Thank you. Hi, everyone. My name is Menzi, and I'm now a postdoc at UCLA. And today I'm going to talk about the CESM2 performance out of the CMIP6 ensemble in a Pareto optimal evaluation of tropical low cloud feedbacks. And this project is supervised by my 2 advisors, Hui and David, and it also receives a lot of help from my colleague Ni, our collaborators Leo and Chuck at GFDL, and Kathleen at the University of Virginia. Next slide. Thank you. Thank you. So thanks to Mark, we have learned a lot about the importance of cloud feedback, and we'll have also see a similar version of this figure in her talk just now. Yeah. And if we focus on the tropical marine low cloud, then we can see it is the second largest term of the uncertainty based on the WCRP assessment 2020. And there is also a large model spread from the 12 selected CMIP6 models in this 2022 paper. So the reason to study the tropical marine low cloud is to understand this large model uncertainty. Next slide, please. Yep. And another thing, thanks to the recent studies of the SST pattern effect, now we have established a picture how the SST in remote ascent regions can influence the local regions. And here is just a simple conceptual model. When the SST in ascent region changes, it will influence the free troposphere through deep convection. And then the signal will be propagated to the entire tropics due to the weak temperature gradient. In this way, it will modulate the estimated inversion strength in local regions. And if the estimated inversion strength increases, then there will be more low clouds, which contribute to a negative cloud radiative effect. And on the right, here is a detailed decomposition of the local sensitivities to local SST and to remote ascent region SST into different cloud controlling factors. We can see similar structures between these 2 major stratocumulus regions, one in Pacific and the other in Atlantic. And if we focus on the sensitivity to ascent region SST, then we can see the dominance of an orange component, which is T700. So we can simplify the shortwave CRE based on just local SST and T700. Next slide, please. Yep, so we can see the first equation. Now we can simplify the change in shortwave CRE as a linear combination of local SST change and T700 change. And there is also a recently proposed low cloud index called estimated cloud top entrainment index, or ECTI. This ECTI index is a combination of estimated inversion strength and the specific humidity difference between the surface and free troposphere. And because this specific community difference is also proposed as the major pathway how the local SST influences low clouds. So we can view this ECTA index as a combination, as a theoretical combination of the SST effects and the T700 effects. And we can also empirically estimate these sensitivities, KSST and KT700, using observations and CMIP6 models. So in these two panels, I'm showing the estimated sensitivities on both axes. The gray bars indicate the sensitivities estimated from series and ERA5 with one standard deviation. And then different dots means different CMIP6 models. And ECTI predict a linear relationship between the possible values of KSST and KT700, which is shown in this black line. If we look at the Southeastern Pacific on the left first, then we can see there is a good agreement between the observation, CMIP6 ensemble, and the ECTA line. And if we focus on CSM2 in the lower right corner, then these models are overestimate the sensitivities to both local SST and T700 relative to observations, but the values are not too far off the observed range. If we switch to the right panel, the Southeastern Atlantic, then we're going to see something more interesting. In this region, the ECTA line deviates from the actual observations, and also most models are underestimate this local SST and T700 sensitivities relative to the observations, while CSM2 models are performing very well, especially the CSM2 and CSM2 vacuum, the high resolution versions. Next slide, please. And we can take a closer look at the Southeastern Atlantic by looking into different seasons. Here I'm showing the results for MAM and SON. During MAM, this is when the connection between the free troposphere in Southeastern Atlantic and the free troposphere in remote ascending regions are strongest. So the weak temperature gradient approximation also works best during this season. And then we also see a better agreement between the ECTA line and the observation values. The CSM2 models are all located within this red circle, so they are again doing very well compared with observations. But because other models are also giving reasonable values, so in this panel, the CSM2 models are not really stand out. If we look at another season, SON, this is when the correlation between Atlantic free tropospheric temperature and the ascending region free tropospheric temperature, the correlation is lowest, then we see a quite large difference between the ECTA line and the actual observations. And again, most models underestimate the local SST sensitivity quite a lot compared with observations, while CSM2 and CSM2 vacuum are giving much better results. Okay, next slide, please. Now we have this model assessment of the local feedbacks in two different regions. If we try to put them together, then we will encounter a conflict. So here on the X and Y axis, I'm showing the sensitivity to local SST in two different regions. And we cannot find a single perfect model which agrees with the observations in two regions at the same time. So for example, if we want to improve the performance in Atlantic by choosing CSM2, then the performance in Southeastern Pacific will not be as good as some other model candidates. Because of this, we are going to introduce the Pareto optimal approach to combine the results in two different regions. Next slide, please. The concept of Pareto optimization means there is no alternative which is better in all dimensions. Or in other words, we cannot improve in one dimension without worsening the other dimension. And we can use the right panel as an example. Here, the x-axis and y-axis represent the model performance in precipitation prediction and SST prediction, respectively. And if the error is smaller, then the model is doing better in that dimension. And the colored circles are individual models, and there are also many gray dots represent small model ensembles consisting of a small number of selected models. And these gray dots in the lower left corner are colored red. This is the so-called Pareto front. And because for these model ensembles, we cannot improve it in both dimensions at the same time. If we want to reduce the error in precipitation, then we will have to increase the error in SST, vice versa. Next slide, please. And we can also look at the Pareto optimization results for our case. And here I'm defining the RMSE in each region as a combined bias in the SST sensitivity and the T700 sensitivity. And so here again, the colorful dots are for individual models, and these gray dots are generated small sub-ensembles consisting of up to 5 different models. And we see a relatively short Pareto front in the lower left corner, which means to some extent we can optimize the model performance in both regions together using model ensembles. And we can see the CSM2 models in the red circle are located on the right side of the data cloud. This is because CSM2 models are outperforming the other models in Southeastern Atlantic. And we can see when we move to the right, we are reducing the RMSE in Atlantic. But at the same time, we are increasing the RMSE in Pacific, which is associated with this trade-off between two regions. Next slide, please. And with the help of this Pareto optimization, now we can try to assign a probability weight to individual models. And I'm using CSM2 as an example. Here, the data points in the red quadrant means the model ensemble are worse than CSM2 in both regions. And the data points in the blue quadrant have better performance than CSM2. So if there are more data points in the red quadrant, then overall CSM2 is performing better. If there are more data points in the blue quadrant, then CSM2 is performing worse. And then we can define the weight as the ratio of red to red plus blue. And this weight will be in the range between 0 and 1. Particularly for the data points along the Pareto front, this weight will be 1 because there are no other models better than this one in both dimensions at the same time. Next slide, please. And then we can make use of the estimated shortwave cloud feedback from the Lincoln 2020 paper. And on the right panel, this blue line shows the original histogram of the estimated shortwave cloud feedback if we assign equal weights to different models. And then we can also update this PDF using the weight we have generated just now using Pareto optimization approach. And this gives us this orange line, and we can see the huge difference between these two PDFs. When we updated it with the Pareto optimization, then the probability of a negative shortwave cloud feedback almost disappears. And at the same time, the probability of a very high shortwave cloud feedback increases a lot. And this is mostly contributed by CSM2 and CSM2 Wacom because of their good performance in Atlantic. So and next slide, please. So we can summarize this CMIP6 model assessment. So first, by using SST and T700 as the cloud controlling factors, we can explicitly account for this remote influence from ascent regions. When there is warming in remote ascent regions, then it contributes to an increase in estimated inversion strength, an increase in local cloud amount, and a negative cloud relative effect. And we see that when and while the weak temperature gradient approximation works well, like in the Southeastern Pacific or like in the during MAM in South Atlantic, then there is generally a good agreement among the models, CMIP6 models, observations, and also the ACTA index. But during SON in South Atlantic, when the WTG approximation does not work well, then most models are underestimate the local SST sensitivity quite a lot, while CSM2 models outperform these models, especially the high resolution versions CSM2 and CSM2 vacuum. And we can use a Pareto optimization approach to combine these model assessment in two different cloud regions. And when we update the PDF of short of cloud feedback, we see a very low likelihood of a negative short of cloud feedback, and there's a large increase in the likelihood of a high short of cloud feedback. Thank you for your attention, and any questions will be welcome. Thank you.
Any questions from the audience, from online? Okay, then thank you again, Mengxi. We will move to the next presentation, with which we will change the topic a little bit. Brian Medeiros will give us an update on radiation.
Okay, well, I thank the organizers for giving me an entire session to myself. That's never happened before. I assume it's because you recognize how important radiation is for the system. What I'm going to be talking about is an update, for most of you, an update on the status of the implementation of RTE, RRTMGP into CAM. This is, and I've spelled out the acronym here. I realize that this is extremely jargony. So that means radiative transfer for energetics is the RTE part. Rapid radiative transfer model for GCMs is the G, and parallel is the P. I recognize that there are some naming convention problems in this name. I wasn't in charge of that. So in our implementation of this radiation scheme into CAM, I've been working on this for a couple of years, and I've gotten help from Isaac, Courtney, Zhang, as well as the Earthworks software engineers, and Robert Pincus, who's the developer of this version of RRTM. So I'm not going to try to motivate how important radiation is for the model and for the climate system. I assume that's why I got the session all to myself, so you know that. But I will try to motivate why we would like to update the radiation scheme to RRTMGP. So normally we drop the RTE part when we say it, just to shorten it a little bit. It's a complete rewrite of the current version of the radiation that we have. So we're currently using RRTMG. RRTMGP uses Fortran 2003 conventions, but underneath it all, it's still kind of the same kind of radiative transfer model. It's still a plain parallel, correlated decay, two-stream radiative transfer model. For those of you who know what that means or care what that means. The rewrite uses classes to control information passing among the different pieces of the parameterization. Explicitly, there's no reading or writing of files within the radiation scheme, so that's the burden of that is transferred to the user to prepare the data and hand it to the radiation scheme to work on. There's no assumption of vertical ordering in the columns, so right now in our radiation implementation, there's a lot of fussing about whether the vertical index is upward or downward, and so there's a lot of reordering. That gets taken care of once you get into RRTMGP, which is nice on our side. For science answers, the important thing is that there's updated spectroscopy included in this model, which means that the fluxes that we get out of the radiation scheme will be more accurate, more realistic. So that's the important science update to the package. What it boils down to is that you have a long wave solver and a short wave solver. These are actually very simple functions underneath it all. The inputs to them are given here. That's basically these complicated K structures that are optical properties. a lot of the work of the radiation parameterization on our end is getting these things put together for the RRTMGP scheme to use. And the shortwave needs insolation, so sunshine, and the surface albedos. The long wave needs, besides the optical properties, it needs the Planck source functions as well as the surface emissivity. And all of our work is basically to get all of our data organized in such a way as to let the radiation work on these things. There's a lot of flexibility added by this rewrite of RRTMG into RRTMGP. And I think that this kind of outlines it. This class structure is extensible, so if we wanted to introduce our own class that takes one of these classes and builds upon it, that's relatively easy. If you wanted to break it up into the RTE part, which is the part that actually does the solving of the fluxes, you can just use that separately. The RRTMGP part, which translates the atmosphere into data for RTE to use, can be taken out and used separately if we needed to. There's also a couple of important features that allow new capabilities. One of them is GPU acceleration. So RRTMGP already has directives in the code to use GPUs. The Earthworks group is making use of this now and testing that capability. And also there's a CCPP version of RRTMGP that's being used in the NOAA model. I haven't looked at that yet, but I assume that as we go forward, we will be able to save some effort. We will be able to save some effort in our CCPization of RRTMGP by taking some of what they've already done. So what's involved with doing this? It's basically we're bringing in RTE, RRTMGP as an external, just like we're doing with Pumas and Club and many of our schemes. So when you run checkout externals, it's going to grab the GitHub repository and download it into your physics directory. The work on this project is basically to do this translation from CAM data to what the radiation needs, take the radiation output and translate it back to what CAM needs to update the model. I inherited a version of this interface from Brian Eaton, who was working with a prototype of RRTMGP quite a few years ago. When I got that, it didn't work with the version of RRTMGP that was current at that time, so I had to start making modifications. A lot of those modifications are inspired by Ben Hillman's implementation in the E3SM superparameterized configuration. The three versions have diverged from each other a bit, but they all share kind of common goals and a lot of common code. Most of what we're doing is just rewriting radiation.f90. That's the main module, but there's a couple of supporting modules. RRTMGP inputs, which basically replaces RRTMG state. Rad constants, which I'm going to suggest we get rid of at the end of this talk. Cloud radiative properties is messed with a little bit. And then there's a really thin wrapper. We basically take this out of the examples directory of RRTMGP and just modify it a little bit. It basically does some error checking before it goes into the radiation. The radiation module just looks like this. Above this line are the public subroutines and functions, and it looks a lot like what we have now in CAM6. So we read the name list, we initialize the radiation, and we call a radiation tendency. We register a bunch of stuff into the PBUF, and we do these restart things to read and write restarts, and a couple of helper functions to figure out if we're doing radiation or not, and a data structure to hold some variables. Most of the on the right side and at the bottom is almost unchanged from the current CAM version. What we're really changing is the name list a little bit, the initialization, and the tendency. A lot of what I've done is to introduce a bunch of these private methods down here that I'm not going to talk too much about. Mostly what they do is reorganize data and initialize or allocate and deallocate arrays to really clean up radiation tend, make it shorter to look at and easier to understand. Inside of radiation tend, there's really 4 stages. They're pretty simple. There's a data preparation stage where we basically figure out if we're going to do radiation, and if we're doing radiation, we need to know which columns are daylit and which are not. And then we get some data prepared for our TMGP, the surface temperature, emissivities, temperature, pressure, sunshine, albedos, things like that. They get prepared on like daylit columns or not, depending on if you're running shortwave. Then you go into and do shortwave and long wave if you're running them. And they both follow this kind of workflow that's parallel to each other. So you determine the cloud optical properties, you basically add them up, you reorder them if you need to get the right band structure that is assumed later. Initialize an object that gets passed into the radiation scheme, set your radiatively active gases, set your aerosol optical properties. So these three things are just getting data prepared, optical properties for clouds, gases, and aerosols. Then you just send it into the radiation, outcome fluxes, you capture them and do a little post-processing to get top of atmosphere, surface fluxes, things like that. Everything goes out into this little short post-radiative transfer step where we do a little bit more output. And the main thing that happens here is that radiative heating rates are deduced from the fluxes. So that's the QRL and QRS that you've probably seen in the output. That's the actual heating tendency that gets passed back to CAM that gets used to update the state. And then we deallocate a bunch of arrays. The current status of this project is that we're using RRTE, RRTMGP version 1.5. It's coming in as external, like I said. Version 1.6 was just released. If everything has gone as well as I think it has, then we can, in one file, we change a 5 to a 6. We check out externals and we run, and we'll be using version 1.6. We'll see how that goes. We've merged our branch, so we've been doing all of this on a separate branch from the CAM development branch, and we've merged up to the most recent CAM development branch as of like 2 weeks ago. To run RRTMGP as the radiation, it's just a CAM config ops string like this. COSP is already active or is already hooked up, so if you want to turn it on, you turn it on like normal and it works. And we've been doing a lot of testing simulations lately. We've been doing SCAM, aquaplanets with finite volume and spectral element dicores, F2000 cases. Zhang did an F1850 case at 2 degrees, and some F-HIST cases. So we're at the stage now where we're doing validation. We're trying to understand if the answers we're getting are sensible. We've been doing this by comparing with the released version, the CMIP version of CESM2. That mixes a couple of things, because as I said, we're on a development branch of CAM, so we're mixing radiation changes and non-radiation changes when we do that comparison. I'll show you that in a second. During this validation, Zhang did some runs and noted that the SOL-N, the sunshine, is a little bit lower with the RRTMGP code than with the RRTMG code. So we're looking into that. That should be a relatively simple fix to recover wherever we're losing that sunshine. But the other thing is that he noticed that in QRL, the long wave radiative heating in the lowest model level, RRTMGP has more heating than RRTMG, and we're trying to understand whether that is a bug and whether it's right or wrong. Just a couple of quick results from some of these test runs. So this is what I'm showing at the top is the time series of global average surface temperature from a F-HIST run in the dark colored line with RRTMGP. The shading shows the range of the CMIP version of the model's AMIP run. So there's like about 10 simulations here, just to show you the spread within AMIP runs. And you can see we're a little bit colder than the CMIP version of the model. That's shown down at the bottom. This is the ensemble mean of those AMIP runs, and this is our run, and this is the difference. So over land, where we're not prescribing the surface temperature, we're too cold. I was a bit worried about this, that we might be messing up the climate, and then I did a run with the same version of CAM, but RRTMG, so without changing the radiation scheme, and we got the same answer. So that's good. We're maybe not screwing up the climate too badly. A similar story for top of atmosphere fluxes. So this is the outgoing long wave on the top, global average time series, and net shortwave at the top of the atmosphere, and then the residual, so restom, which is what we're always looking at to see the imbalance maps on the left. And again, with RRTMGP turned on, we see a substantial decrease in both of these top of atmosphere fluxes and a much larger imbalance at the top of the atmosphere. But when I ran it with just the regular CAM case, without changing the radiation, it's actually quite a bit worse. So this is not a perfect comparison. I'm not going to go into the details, but it gives me some hope that with the new radiation, we haven't gone off the rails too badly. The panels don't show this, but the orange line is CAM development without RRTMGP. So yeah, I forgot to change the maps. So we're going to look into this sunshine issue and this long wave heating and the lowest model level issue to see if they're correct or not, and see if we can make them match what we expect. And then I think at that point, we're ready to move RRTMGP into the CAM development branch as an option for now. Longer term is where we're going to need some help, I think, and that's moving to the CCPP version of RRTMGP. That's going to require basically taking the entire interface that I just spent the last 2 years building and taking it apart and getting rid of it. That'll be good. But importantly in this is that we're going to need to rethink how the cloud optical properties get set in a CCPPized version of CAM. And we also need, when we're doing that, we should be thinking about how we interface with those optical properties, because right now they're lookup tables that are tied to the RRTMG band structure, and it just assumes that it's hard-coded. Part of that hard coding is in rad constants, and I'm going to suggest that we get rid of rad constants altogether. All of these hard-coded values should be coming in as part of the treatment of radiation and cloud optical properties, and can be set at runtime. The GPU acceleration is happening in the Earthworks project, so that's going forward. And at some point, I think that because of the GPU and CCPP options that we will have I think eventually we'll want to change to using RRTMGP as the default radiation and probably the only radiation that we support. So I'll stop there. Thanks.
Without radiation, we would a huge chunk of contents in the previous block of talks.
Yeah.
That's right. That's a possibility.
All of the water would freeze out and would be any clouds at all.
All those cloud forcing diagnostics, cloud feedback diagnostics. That's why you get your.
But then the dynamicists would be so happy.
Rich?
Can you say a little bit about the solar in problem? Is that a top of atmosphere surface?
That's top of atmosphere, yeah.
Is that just a data set problem then?
So it's something that, so I'm trying to use the same data set that's being used currently in CAM, and something, I think what happens is that there's some different assumption at the top of, in the extra layer above the model.
Right, got it.
So we're getting a little bit more scattering than I expected by making a different assumption about what happens above the top of the model.
Julio has a question.
I hate to use, hearsay, but I've heard that RRTMG had trouble with very warm climates in the past and things like that. Have you heard this, and is RRTMG-P not subject?
I have been told by people who know things that there are, at very, very high CO2 concentrations, RRTMG is not a valid solution. I have been told by other people who have done experiments at very high CO2 values that it seems to be okay.
Okay.
I'm not the arbiter of who's right in that debate, but the RRTMG-P spectroscopy is valid at a larger temperature range, and I think a larger range of gas concentrations. Dustin?
I know I've asked you this before, but have you looked at the performance of RRTMGP compared to RRTMG?
So up till now, I have only looked at it briefly, like as we're doing these testing, and it seemed like it was only slightly slower than RRTMG. When I was doing these last runs, like just within this last week trying to do some testing, it actually seemed faster with no other changes. So I'm not sure I think there was something else going on with those.
Okay, because we're stubbornly stuck in the UFS and the CCPP with RRTMG being about 3x slower, and we just can't seem to.
Are you using the lower number of G points?
Yes, we're doing the same number of spectral points as we were doing in RRTMG.
I will do some more careful runs once we patch up this latest merge to check, but I feel like we were getting like maybe 10% slower, not a factor of 2.
That's encouraging.
Speaking of performance-related stuff, you
you showed that you were like allocating and deallocating stuff. Is that happening every time step, or is it just happening when radiation's called? Is that happening all in the beginning end of model?
When radiation is.
You don't know if you talk about it after.
That's a good question. It might be every time step. Some of it will be when radiation's called, but some of it will be every time step. There's an allocation of fluxes and a deallocation of fluxes. And then there's some other stuff that happens when radiation is actually running that gets allocated and deallocated. The important thing for us along the way was that we have to make sure that we deallocate those arrays, otherwise bad things happen. Cool, thanks.
Great talk, Brad. I'm curious what you need for liquid and ice optical properties. Like what variables are being pulled in from that lookup table, and is there any opportunities for some of the very fancy observations that are made to help with that problem?
I would like someone else to answer that question. There is I don't know.
Okay.
The lookup tables look pretty complicated to me, and I think that they have some angular dependence of absorption and scattering in different bands, but I don't quite understand
I know
where they come
some
from
people
or who
have
makes them.
taken like very detailed measurements of ice crystals or liquid and run other radiation schemes on them to determine kind of better estimates of the optical properties. So maybe that's an opportunity to reach out with them, those groups.
Yeah, I'm not sure who's doing it. I know, I did talk to Robert recently, and one of his students is working on a side project that would potentially supplement our optical properties values, which might be one avenue forward. But I honestly, where we get the values that we're using right now, I don't know where they came from. There's no metadata in those files.
That's fun.
Your second point that you say you have to deconstruct the interface that you've been working years on. I just curious why you say that, because in the case of Club, for example, we have a lot of code to kind of prepare before we actually call the Club external, which will probably be turned into a quote-unquote parameterization.
Yeah.
Don't you think this would be a similar thing, or is there something else going on?
I think it will be similar. I think it might be more dramatic in this case, because I do think what the right answer is to get the cloud and aerosol optical properties completely out of this and have them be separate. So you'd have in the suite, there'd be like a get cloud optical properties, get aerosol optical properties, get gas optical properties, then maybe some thin version of what we've got here to put them together, and then radiation.
That's different.
You've got this insight, and then you pass this insight on to Jesse.
Yeah. Yep. Thanks, Jesse.
I think you thank Courtney.
Okay, is there any question online?
No.
Okay, so then that concludes our morning session, and we should go to lunch and charge ourselves. And we will start again at 1.
No, at 12:45.
12:45, okay.
Is the talk not on the published? Yeah, no, there's a mistake. There is a talk, it was added last week. There's a talk at 12:45. So, sorry for abbreviating the lunch, but.
It's on the online.
It's on the
online agenda has it, yeah.
Okay, great. So should we?
think.
Let me,
Could you hear me? But maybe I can just share my screen.
we can hear you very well.
Okay.
Can you hear me better now?
Yeah, a little bit.
Okay.
So I cannot share because someone is sharing the screen.
Okay. All right,
Still, I'm not allowed to share my screen.
Could be.
we can also, well, they're gonna try to fix that, but we can share, we have your presentation, so.
Okay, I think I can make it. Yeah, now I'm allowed to. Okay, that's awesome.
All right, everybody, welcome back.
Oh my God, this is not the right screen. Could you see my presentation now?
We see a directory.
Oh no, that's not the right one. Okay. So I'm gonna try again. Sorry about this. Okay, I'm gonna share the entire screen, so hopefully that's gonna work.
If you could open your talk up on the background and then just share that window.
How about now?
There you go. So yes, our first talk is from, this is a session on boundary layer processes. And our first talk will be from Sarah Shamek on dimensionality reduction. I think we're already at 12:46, so you might as well, yes, why don't you go ahead and start, Sarah?
Could you see it in full screen?
No, right now it's not in full screen mode yet.
Oh my God, sorry about this. Yeah, I'm gonna figure it out. Just a second.
Yeah, I think if you go to the top slideshow.
Yeah, so in my screen it's in a slideshow. Oh no, sorry about this.
See it pretty well in the normal mode like this.
This is pretty odd.
So do you have two monitors?
I have one monitor.
Okay. Are you mirroring your talk, or do you have presenter mode on your side?
Well, I have presenter mode in my side.
Yeah, you need to switch those. Or just mirror your talk if you can.
Okay. Let's share this entire screen. Maybe that's gonna work better. Okay, how about now?
That looks good.
Is it good?
Yes.
Okay, great. Thanks so much, and sorry of the trouble. So I'm Sarah, I'm postdoc at Columbia University, and I'm very happy to tell you about our work on using dimensionality reduction techniques to parameterize and decompose the vertical turbulent flux of the scalars in convective boundary layer. So the idea is that our climate models or our kilometer scale models that have grid size of, let's say, kilometer scales, they do not resolve any processes smaller than their grid size. And then we have to rely on parameterization. And for the case of convective boundary layer, the important parameterization is the vertical turbulent fluxes. And we usually approximate them as a function of the resolved variables by the model. One of the very common parameterization for convective boundary layer is eddy diffusivity mass flux that assumes that the smallest scale fluxes or the smallest scale turbulence can be approximated using an eddy diffusivity. So this first term, if you could see my mouse, and then the impact of larger scale eddies or coherent in structure in the vertical turbulent flux can be parameterized using a mass flux term. However, these parameterizations are usually one of the main sources of climate models uncertainty.
One of the reasons is that they sort of like overestimate the entrainment flux. So here I'm showing a plot that I took one of the mass flux, a diffusivity mass flux scheme that is used in ECMWF, and I try to retune it to give the best results for my LES data. So here in the solid line, we see the LES data, the LES output for heat flux, and then the solid thin line is the eddy diffusion term, sorry, the eddy diffusion mass flux. And we have also the each term like eddy diffusion and mass flux separately. And what we see is that we have sort of like overestimation in the inversion layer. We have a very large negative flux. So that's basically this overestimation of the entrainment flux. And probably the reason is that these models, they do not explicitly take into account the entrainment flux. And they do not generalize to situation with a strong wind. And then they also sometimes some of the underlying assumption may not hold. For example, the of coherent structure may not be negligible. So for this work, what we thought is to develop a data-driven parameterization a data-driven parameterization of vertical turbulent fluxes using reduced order representation of turbulent kinetic energy and a scalar profile. And we want these parameterization to generalize across the turbulent regimes. So let's say going from weakly to strongly convective cases with different wind shear. And then we want this parameterization to model the vertical fluxes of various scalars, for example, potential temperature or passive tracers. And also we want this model to decompose the vertical turbulent fluxes to two main modes of variability based on the origin of the turbulence that we could say. So I have three assumptions that I want to discuss them first. So we assume that all scalars are transported the same way by the flow. For example, if X represents my scalar, I assume that the turbulent flux of this scalar as a function of only the scalar profile and TKE, and this F doesn't depend on the profile of X, but only on the flow. So if I have, for example, potential temperature and a tracer, both of them could be modeled using the same F. Then we assume that we can approximate the vertical turbulent flux using two main modes of variability. So this is simply the same assumption that made by many of the parameterization. For example, eddy diffusivity mass flux has two terms, the diffusion and the mass flux, or eddy diffusivity counter gradient parameterization has the same assumption. And then we want these two modes, one of them to be dependent only on the horizontal TKE, so that's my F1, and then the second one to be dependent only on the vertical TKE. And both of these F1 and F2, they have also my vertical scalar profile, the vertical profile of my scalar as input. So to have the data for this study, we run large eddy simulation that represent dry convective boundary layers. So we have two larger scale parameters that we change. One is geostrophic wind, and then the other one is surface heat flux. So geostrophic winds go from large to small, and surface heat flux goes from small to large. So we have simulations from weakly convective strongly shear to really strongly convective. And we have 6 simulations with these conditions. And then to prepare the data for training a neural network that is supposed to approximate the function that we want, we horizontally coarse grain our data and then compute the mean variables and the turbulent fluxes. Within this simulation, I have implemented 3 tracers. One of them has a height dependent profile. The second one has a source at the surface. And the last one has a source in the free troposphere, so entrainment force tracer. And the idea is that our neural network that we want to train for this work should map all of the scalars that we have to their corresponding fluxes. So I have 3 passive tracers, my S's, and then I have also my TKE and the potential temperature. I want to predict their corresponding fluxes. So we develop a novel neural network that is trained on all 5 scalars together and 6 simulations that represent different instability parameters together as well. So the model that I have has a structure like this. So I use what is called encoder-decoder. They are sort of like nonlinear dimensionality reduction technique that are very powerful in capturing the structure in the data. And what I want to do, I want to pass TKE, the vertical profile of TKE, as input and ask that neural network to predict the TKE, the horizontal TKE. So that's for the upper branch, and the lower branch takes the TKE as input and predicts the horizontal, the vertical TKE. So the idea is that if we look at the TKE, probably there are some information within that profile that a nonlinear dimensionality reduction model could capture that. And we see that in our prediction that this is actually true. We can have only total TKE and predict the horizontal and the vertical TKE. Now, the interesting fact is that the input, the size of my input is 128. So that's the layers in my larger D simulation. And this dimensionality reduction technique first mapped that high resolution input to a low dimensional representation that I refer to that as Z of TKE U or Z of TKE W. And the dimension of that low dimensional representation is only 2. So we can compress all of the relevant information in a 2-dimensional space. And in the second part, what I do, I take that low dimensional representation and I want now to predict my fluxes. But I still have to have the information from my scalar profile. So I compress my scalar profiles as well. And then I have 2 decoders. One of them takes Z of TKE U in Z of X, and the other ones that take Z of TKE X and Z of TKE W. So I sort of like separate the information related to horizontal and vertical TKE and use them with decoder to predict the total flux, but also to somehow approximate what is the contribution of each of these 2 terms to total flux. So some results, here is the prediction for vertical heat flux. So I'm showing one case that is strongly sheared and the other case that is strongly convective. So and then the solid line shows the prediction, the dashed line shows the true value, and on the left plot with the colored line, we have cases that are sort of like out of equilibrium. So they could be like strongly convective or like weakly convective compared to a situation in equilibrium. And we see that our model is capable of approximating that profiles as well. So this model is trained on all 6 simulation and all 5 scalars together, but here I'm showing the results only for 2 simulation and one of the profiles. Then I have a comparison with EDMF. So here the solid line shows the EDMF, the dashed line shows the LES, that's my ground truth, and the flux NN is our neural network. And I'm showing on the first plot the heat flux, the second one is surface force tracer flux, and the last one is entrainment force tracer flux. And the color shows 2 simulations. So our model sort of like very closely follows the ground truth. And based on the equation that I had, I can also decompose, or I can also plot the decomposition that we have. So the first mode that depends only on horizontal TKE, we refer to that as shear mode. And the second mode that depends on vertical TKE, we refer to that as convective mode. And if I plot them, we see that they are sort of like consistent with our expectation of the sources of turbulence in shear-driven and convective-driven boundary layer. For the shear mode, for example, the simulation with lower instability parameter, they have a larger contribution from shear mode and a smaller contribution from convective mode. And the inverse is true for the convective mode. And then we also can look into the inversion layer, and we see that the simulation with large wind shear has a larger amount of larger contribution from shear mode into the flux, and the simulations with strong surface heat flux has a larger contribution of convective mode into the inversion layer flux. And then the last part is how much of these 2 modes that we find are diffusive. So here we do a simple projection, the projection of each of our mode onto the profile of our scalar. So we can then compute the diffusive part of the flux, but also we can approximate the eddy diffusivity. And a constraint that we impose here is that this K that we want to approximate should be the same within the same simulation, but not necessarily between the simulation. So here is the result. If I project my convective mode into the gradient, I see that near the surface, I have a contribution from the diffusion, but then within the mixed layer, this contribution goes to 0. And the same is correct for the shear mode. I have a large diffusive flux near the surface or in the surface layer, but then the diffusive flux becomes 0 above the surface layer. You can also look into the eddy diffusivity. So here I have the approximation of eddy diffusivity for convective mode and for shear mode. And it's sort of like 3 times smaller than the previous approximation of eddy diffusivity. Okay, thanks so much. And that's all that I have. And I'm looking forward to your questions and comments.
Are there any questions? Well, I have so you would propose this would become a parameterization in terms of fluxes, not, it looks like the diffusive part is not a good representation of the fluxes. So can you envision this becoming a part of a model?
I do. I think that's a great point. So what we find is that actually we cannot really approximate the flux using a diffusive model. So I started like using a local model that is really forced to maximize the diffusive flux, but that didn't really work. So in terms of like implementation, one further step that I have to go is to come up with some analytical forms for this representation that makes it way more simpler for implementation in a model. And also it makes it easier to sort of like have an upper bound and lower bound in order to control the amount of fluxes that we have.
There's a question from the virtual world. Leo.
Yeah, thanks, Sarah. I wanted to ask this question. So you built on the mean state and the turbulence kinetic energy. And I'm just thinking at one of the ideas, at least behind EDMF, even though if in practice it's had some problems with its performance, but there's the idea that the mass flux part of it may be linked to the surface flux. And I'm just wondering if you could envision applying this general technique, but in addition to bringing in the mean state and the turbulence kinetic energy, also factoring in, say, the surface heat flux.
Yeah, that's a great point. Thanks so much. So yeah, so that's one thing that I want to do, like that's the next step. So I have the modes and I want to predict them using really few variables. For example, let's say geostrophic wind, surface fluxes, for example, if that's heat flux, surface heat flux, and then probably some variable related to the entrainment flux as well. And if we could do that, then that would be a simple but more probably like really accurate model. But that's a great point. That's something that I'm looking forward to do.
Okay, great. Thank you.
All right. Thank you, Sarah. I think we'll, in view of the time, we'll move on to the next talk, but thank you very much and for agreeing to present from Europe. Thank you.
Thank you.
So our next talk is from João Teixeira. Are you on, João? It's also remote?
Yeah, I'm on. Can you hear me?
Yes.
Do you want me to try to share or do you want to just, but you have my PDF, so.
Right, why don't you try to share?
Okay. What do you see?
Looks good so far. Can you
see my? What about now? Do you see the presentation mode?
Yes.
All right. So thank you for the opportunity. To give you, I'm going to just give you a brief sort of highlights on recent developments of the TPT project that tries to sort of unify boundary layer and convection parameterization. This is a list of all the co-authors. I'll be rather quick on every slide, so if you have questions, you can ask me later or we can go for discussion. I'll be around until the end of the session. So our CPT, overall, the main goal is to reduce key biases related to PBL clouds and deep convection. The idea is to try to develop and implement unified parameterizations, essentially based on EDMF concepts, but as you can see, we've extended that during this project. And we are focused on PBL transition and transition to deep convection, both from sort of a spatial transition perspective over the ocean, but as well as a temporal diurnal cycle transition over land. I'm the lead PI at UCLA and JPL, and we have a bunch of PIs, Julio Bachmeister, Leo Donner, Rong Fu, George Mateo, and Michael White. So I will start with a couple of slides of highlights of not necessarily the NCAR model, but then most of the presentation will be about the NCAR model. So one of the things that we've invested a lot, and the community in general, we are not doing this in a different way than anybody else. We're just doing it, I think, using more sort of sophisticated LES experiments, high resolution, bigger domains, that sort of thing. But we do a lot of large eddy simulation. That's at the core of a lot of what we do. George Mateo from the University of Connecticut and his team are sort of the main team responsible for that, although there's a little bit of work on at JPL and UCLA. And George has done wonderful LES simulations, as many of you may know. One that I wanted just to briefly highlight comes out of a paper that he wrote with Umayma Lamarkel. And what they looked at was a convection organization. And in this slide, so don't worry so much about the row above, but the second one, actually, if you can, I hope you can see my my cursor. So you have three simulations here at the bottom. The first one has a domain of 40 by 40 kilometers. The second one has a domain of 80 by 80. And the last one has a domain of 160 by 160 kilometers. George has now extended this and is investigating a much, much larger domain. But there's a couple of things you immediately see here. You can see these very complex structures, mesoscale associated with cold pools and that type of dynamics that you see in the larger domain. But of course, because these structures are bigger than the domain of 40 by 40 kilometers, you don't see it in the smaller domain. So a lot of what George has explored and his team have potential significant impacts on parameterization. Not only the fact that a lot of the LES simulations done up to the moment often come from very, very, very small domains, much smaller than 40 by 40 kilometers. So in a certain sense, are not really representing, they don't have a domain that is large enough to sort of represent a lot of the reality that we know exists. But also he had looked at things like the fluxes and the vertical velocity and how things actually change across the different experiments. And he saw a lot of interesting similarities that are kind of, as I said, have a potential significant impact on parameterization. Now, our colleagues at GFDL have explored over the last several months in a lot of detail different diagnostic approaches to understand the stratocumulus problem. So while they have also been implementing a version of EDMF, they have also explored this other side, which is trying to understand better what is it that leads to sort of the biases that are experienced by the GFDL model in terms of stratocumulus and other models as well. And this is a figure that is sort of, there's a lot of lines, but there's sort of a reason to that in a way. So what you see here in the vertical is liquid water path. This is just single column model or LES simulations of the stratocumulus DICOMS RF1 case. And you have time in the horizontal. You have the observations. This is based on a field experiment off the coast of San Diego. The observations are here close to about 80. And you have a variety of colors. Don't worry too much about the details. The main story is that the black one, the thick black one, gives you sort of the mean, ensemble mean of several LES simulations from using different models from the Stevens et al. Paper from 2005. The different colors represented, you can see it here at the top right, that they represent different either single column model simulations using the GFDL model or LES simulations using the model that George Mateo has developed and worked over the last few years. The important message, the most important message I think here is that all these results are produced with very plausible forcing. So there's nothing particularly odd in terms of the forcing that leads to these different simulations. And they basically, the different colors represent either slightly different large-scale forcings, in this case usually vertical velocity or divergence, and different radiation schemes that create this perturbation, but that's not necessarily the main part of the story. So this is an important point because when the GFDL team tried to estimate large-scale forcings from observations, from reanalysis, from AMI-PRUNs, they are quite different. And they do have a significant impact. And the models are showing some sensitivity. So the GFDL model, the single column model, shows significant sensitivity to large-scale forcing and to the radiation scheme, while the LES doesn't seem to show so much of a sensitivity. But this sort of interplay between the large-scale forcing and the sort of small-scale physics, and how do you actually reproduce it with LES, with reanalysis, with amiprons, with nudge amiprons, and single column model, is sort of at the core of this effort at GFDL right now. Let me now turn to NCAR and speak a little bit about, talk a little bit about what we've done and implemented. So the key concept of VDMF is this idea that you sort of bring together in one single parameterization the representation of sort of small-scale mixing represented by eddy diffusivity and sort of large-scale plume mixing represented by the mass flux. And the version that we've been using is one that has been developed at JPL and UCLA for the last 10 years. The essence of this version is this idea of multiple plumes, the idea that different types of convection can actually coexist in the same model grid box. So you can have, plumes that don't go very far, that basically die out pretty early and sort of represent the mixing in the subcloud layer. Others will become shallow convection, others will become deep convection. And a lot of this depends on two factors. On the one hand, we sampled from surface layer thermodynamic properties, and so certain plumes may actually be more active and energetic from the beginning, from birth, so to speak. And we also have a stochastic lateral entrainment that is partly inspired by a paper by Brompton Kwang, in which we sort of stochastically determine how often and how strong are the entraining events that each plume suffers. And so those two components basically lead to this important result that you can actually have in the same grid box a variety of different types of convection, that you don't have to have triggers or thresholds or transitions that are somewhat artificial. And we brought this into the NCAR model in a different context. So what we've done was to try to take advantage of CLUB, which are already doing a lot of great things, but also trying to complement CLUB in what CLUB is apparently not able to do. So, and I'll show in a schematic just after this, that CLUB, while representing double Gaussian mixing, it does miss some of the skewed part of the distribution. And again, I'll show on the next slide. While these MF plumes, these discrete plumes, end up representing that skewness of the distribution relatively well. The way we actually implement this in practice is go to sort of the guts of the scheme. We go to the numerical solver. We go to the 5 diagonal prognostic solver that exists within the CLUB core, and we add these terms to the equation. So the mass flux terms are helping to solve at the same time, are in the same solver that solves for the mean values and the fluxes from CLUB. So the figure I wanted to show is the next one. In this one, this from the paper of Michael White that we published about 6 months ago. This is basically the perturbation in total water. You can see it here in the vertical axis. In the horizontal axis is the perturbation in terms of the liquid water potential temperature. So basically for the LES, this is a cut across a domain of the LES at about 730 meters high. This is the BOMEX case, so this is sort of a canonical shallow convection case. So this is really in the middle of the convection layer. And you have about 3 components that are shown here. One in sort of light gray, you see the joint PDF from the LES. So this is the histogram of all the points that we collect values of, total water and liquid water potential temperature. At the same time, we also show the CLUB joint PDF that is parameterized at that time, and then the location in this sort of phase space of the mass flux discrete plumes. And what is quite apparent is that while the LES joint PDF is essentially a Gaussian, it also has a skewed part of the distribution that is kind of important. And that's where most of the mixing is actually taking place during shallow convection. And CLUB is not able to, in spite of the fact that it supposedly does the 2 Gaussians, is not in this case able to represent that very well, and that the discrete plumes come and take it over and in a way end up representing in a sort of very physically intuitive way the convection that takes place in that sort of that part of the distribution. So we've done a lot of single column model experiments. We also have done 3-dimensional experiments. I'm going to show you just 2 results just to give you a flavor. And then I'll show you one last slide about what things that we are focused on right now. But this is this is an amipron of about 20 years. And we show you again to observations the annual mean low cloud cover. So at the top, you have the observations from Calypso, then a control CLUB at 32 levels, a control CLUB at 58 levels, and then CLUB plus MF. And what you can see when you look at this is that the club at L32 really does underestimate clouds, in particular in the stratocumulus regions. They're sort of very much absent compared to the observations. That increasing the vertical resolution as expected, and as has happened in other models, it does increase the amount of cloud. But in a certain sense, it almost seems to increase it a bit too much. And then Club MF kind of maintains the stratocumulus, but also sort of reduces some of the other cloud cover regions for the sort of the positive bias. So in a certain sense, it doesn't seem to make it worse, and is actually better than L32, probably a little bit better than L58. Now, the key aspect, and I want to focus that on the next slide, is the fact that Club MF in all these simulations does not have an explicit deep convection parameterization. So all of these runs that we show you with Club MF, they do not have Zangwill-Farland. The deep convection is done with the boundary layer scheme, with the shallow convection scheme that basically represents all different types of convection and vertical mixing in the atmosphere. And while the low cloud cover kind of shows you where you are in terms of representing sort of the canary in the coal mine of how well you represent the PBL atmospheric thermodynamics, if you really want to look at the overall thermodynamics, it's obviously very important to look at the precipitation to see how well we are actually doing deep convection. And again, the same structure, we have observations at the top, L32, L58 control, and then Club MF. And if you look at all of these different simulations and compare them to the observations, they are not too different from each other. And in some respects, Club MF seems to be better in some places, not as good in some other places. But it doesn't seem to be clearly worse in any way. And this was a result that was very encouraging to us, which is that we do this without explicit deep convection. So Club MF is doing the deep convection. So this combination of club plus these discrete plumes allows some of these plumes to actually play the role of deep convection plumes. So last slide before the summary. The results that we got are very inspiring and I think very reassuring that we're doing the right thing from a climatological perspective and mostly over the ocean. When you look more carefully at things like the diurnal cycle over land, then there are problems. But of course, there are problems in general with convection schemes over land. So this is just one example, and if you give me 30 seconds or 60 seconds, I'll try to explain this. So this is the LBA case. This is a diurnal cycle of convection and precipitation over the Amazon. These are hours time from the beginning of the simulation. Imagine the beginning of the simulation is some local time, early morning. And what you can see, if you focus first on the row at the bottom, you can see the top of the convection, the mean top of convection height, and the cumulative precipitation for two types of experiments, one LES experiment and one, or a variety of what we call EDMF experiments. This is sort of the JPL version of EDMF, which is in terms of multiple plumes pretty much the same as we have at NCAR. But what you can see is clearly that around 2 hours after the simulation starts, you start to have shallow convection and it gets deeper. And as it gets deeper, as you would expect, around hour 4 or 5, you start to have significant precipitation. Now at the top, what you can see is actually a comparison. This is using SCAM. So a comparison between two versions of Zangwill-Farland and a version of Club MF. Not exactly the same version that I've shown you in the slides before, but actually one that has a slightly different way in which we calculate a particular length scale that we use for the lateral entrainment. And we do it in a little bit better, more dynamical way. And what you can see that as of right now, we do have a representation of that transition from shallow to deep convection, including the depth of the cloud and the amount of precipitation that is much closer to the LES results, which are sort of the black lines at the bottom, than the deep convection scheme that is currently in CAM that has some sort of a very strong initial trigger that ends up being too early and leading to too much precipitation. So I'll finish. I won't read all of this. The last two bullets are the ones that I felt that I should say at least something for a couple of seconds. The current research right now is focused on the downdrafts that are induced by evaporation of rain, diurnal cycle of convection over land, as I discussed and showed, and also more dynamic approaches for lateral entrainment, which is something we need, but I think we know where to get it and how to develop. Finally, the general conclusion is that we've been able with Club MF to actually develop and implement a fully unified parameterization that really does PBL, shallow, and deep convection in a global climate model. Thank you.
Thank you, Joao. We have time for one or two quick questions. Well, I have maybe an unfair question for you. In the sensitivity that is seen in the LES to domain size, are those using doubly periodic domains?
Yes.
So it's possible there's gravity wave modes that are being excited?
Yes. No. So right. These are the simulations do exactly what we typically do in terms of boundary conditions, and often there are gravity wave problems. Yes, no question. But they are homogeneous. They are homogeneous. So in that sense, it's not too different. It's a bit different than if the boundary conditions at the bottom boundary conditions were not homogeneous.
Right. But there's all sorts of sort of horizontally inhomogeneous forcing going on that could be exciting gravity wave modes that will show up differently in different size domains.
Absolutely.
All right. Oh, well, thank you, Joao. I think we'll move on to the next talk from Rich Neal on ZM.
All right. Are we doing microphones? Yeah.
I think, yeah.
Can you hear me? Is that on? Is it on? That's a big one. All right.
Are we not sharing?
Let me check.
Okay.
Yours? Great. All right. Thanks. Okay. Nice follow-on, I think, from Joao's talk. I hate to think I'm flogging a dead horse, but there's been some interesting things I've noticed in ZM, and this is with, I'm sure Cecile will help me with at some point with this, so I'll put a name on it. So there's two things I want to talk about in terms of the way we've modified ZM scheme with respect to potentially CAM7, but there's also another interesting part, a bigger part of this talk that I'll talk about. So essentially, moving into CAM7, we're going to be 58 vertical levels. So you can see this distribution here compared to the existing 32 levels. And one thing that we noticed right near the surface, not noticed, but we knew that there was a very thin surface layer. And the consequence of that from the deep convection scheme, we can see on the right, which is from single column simulation, Togo core, so deep convective West Pacific wintertime. And so what you see if you were to successively use higher and higher vertical resolution, these are the tendencies, just a PDF from the 20-odd day simulation every time step. These are the tendencies you see in the lowest model level. So with 32 levels, it's only reaching 5 to 10 Kelvin, but then through 48, through 58, we're double digits, and then, extreme case here, 256, where it's not converging essentially, and they're becoming more and more extreme values for near surface heating. So that seems like, poor characteristic to use in the model. And so what we did was to essentially moderate that below cloud excessive cooling, which results from always seeing these convective parcels launch from this lowest model level, because the algorithm for finding the launch level almost always puts it in that lowest model level. And so what, the bottom line is what we did was moderate that by mixing levels, but within the boundary layer to provide the level and the properties of the parcel. And so when you do that, it kind of collapses to, 0 to minus 10 Kelvin cooling in that lowest model level. And it's equivalent for all these resolutions. So you kind of, if you like, introduced a scale away, I hate to use that, but you've introduced a scale of this below cloud cooling. So that's, it's important to know, actually, on the previous one, this was on the right-hand side here. These were all offsets by, you can just mirror that, warmings from club. So club responded to this on a time step by time step basis with up to plus 50 Kelvin or so in these extreme cases. Now, that's that first piece. And what was also thinking about with 58 levels was, you can see here ×2 in terms of the vertical resolution in the mid-troposphere, so like 2 times thinner levels. And given the way that the ZM scheme responds to stability in the vertical levels, I took a look at what the potential consequence of that could be. And just to preface, looking at sensitivity with important aspects of convection. So, convection, all the way back to Toga core, these typical vertical heating profiles that result convective, these Q1 type terms, mostly convective contributions. And essentially, it tended to be a maximum around 450 millibars and, with a cooling, with the 0 degrees C level of around 550. So all the dominant heating occurred above the freezing level. And if you looked at a time series for a Toga core period, you can see that most events occurred, maximized in the Q1 term around 450 during, both during light precipitation and strong precipitation periods. And then, what kind of motivated me thinking about this, if you look at our succession of models that we've moved through over the years, 20 plus years, so CAM3 through CAM6 and CAM6 L58, we can see that if we look at again, running the single column model through this Toga core period, we can see that the heating profiles have changed pretty dramatically in the vertical. Heating, as in the convective, deep convective heating, has gone from, of order 3 or 4 Kelvin per day for the period through, hardly any deep convective heating above around 450 millibars. And so that 450 millibars, you remember, is the peak in heating. Now, if we look at the time series of that, for example, this is where CAM6 L58 is. These are both the same Toga core periods and then back through CAM3. And we can see that, predominantly now the heating is below this cooling level. There are periods where it goes, higher, but essentially we've entrained our way, if you like, because of this increased entrainment in CAM6, increased sensitivity, and to increased entrainment. We've kind of moved our way through from a deepish environment to a shallow environment. So I've been thinking, how can we moderate this to a certain extent? And obviously, as always, I'm not the first person to think about these things. And there are many ways we're trying to desensitize this high vertical resolution version of CAM to stability layers. And one way to do this, I think, is to think about how the dynamics of the parcel are happening with reference to ascending parcels that are determined from ZM. And so, there are a number of ways to implement a vertical velocity equation, a kinetic energy consideration of parcels related to buoyancy, related to plume size, and I'm not going to, ultimately that may help, but right now I'm just going to consider a simple kinetic energy, total energy equation, which relates to kinetic energy of the parcel and how potential energy via buoyancy is converted into kinetic energy through some very single value efficiency, and then how you accumulate that in the vertical from the previous layer, and then you consider some of the large-scale kinetic energy. So essentially, I've implemented that into ZM, and to see how that changes things in terms of vertical heating. And so the properties that come out of that, so this is a set of 4 runs that I'll show each time, and the red is a control, CAM6 in this case, L58. And then the blue and the green are separately the green is putting that first near-surface parcel PBL representation in. The blue is just putting this kinetic energy parcel representation in. And the purple is putting them both together. So the blue and the purple only have the KE, so you can only see the parcel distribution in the vertical from those 2 simulations. And you can see that you start from an initial parcel value of kinetic energy. That can be a number of different things. It's a constant in this case. And so in this particular case, there's on the whole, a lot of buoyancy, positive buoyancy cape. And so
with just the K parcel, this is a very strong increase in kinetic energy, but the most important one I want to focus on each time is this purple one, which is the combination of these two changes. So that if you look at the mass flux, you're moving from, in L58, this red case where it's a very low level maximum to, to very small values in the upper troposphere, to something that, in my mind, looks much more realistic, which is, an increase from the surface to its peak level, 500, in this case, 400 millibars here, and then a drop off, which is kind of what you expect. So in terms of heating profiles, we can see here a similar kind of total heating plot I showed before as a point of interest. Here, this is average. This is in the red case with no surface parcel modification. You're off the chart, minus 50, minus 20 Kelvin. And then when we moderate that, we can see here in the, when we include this PBL in the green and purple, it's a small increase over a deeper layer, decrease, sorry. But, the bottom line is when you include this KE representation, which is in the blue and the purple curves, then we get a much a stronger, deeper heating related to deep convection. And you can see, again, just stretching this Toga core case out, where we had this kind of odd bumping up along this 500 millibar layer. And now we can see, this turns out to be a rainy period, now we can see that we really do have this, to my mind, much more coherent vertical distributions of total heating, convective heating. It's smoother. It turns out with just the surface parcel representation, it does get a little bit noisy for reasons I won't go into, but essentially by allowing the initial parcel to be instrumented with a kinetic energy, a vertical velocity, that helps smooth things. Of course, that happens because that's not a total heating. Total heating is pretty equivalent between these four. It has to be in a single column model pretty much for it to be kind of in equilibrium. What tends to happen is the large-scale heating, in this case, it's club, through condensational heating from, the kinetic energy, not boundary layer, but like turbulence scheme, sorry. And so we've kind of mostly reduced that in this particular case. You could argue that's too much. You could say that maybe there is some large scale, and then it comes back to the balance of large scale versus convective heating. TRIM has this large scale component, convective heating. You could say it's like 3-to-1 or something like that for convective in certain environments. So there's an argument to making this a little bit weaker, this impact. But this is now the humidity tendency from deep convection. And so in this kind of control L58, we're convecting and then we're dumping a ton of water vapor at the top of convection. Whereas in reality, in this new version, that happens occasionally, but for the most part, in these deep cases, there seems like some stable cases, but this kinetic energy instrumenting of the parcel allows it to go beyond these single level stable layers, which I think is more realistic. 4 minutes. So just to illustrate that as well, this top level here is the top of deep convection, the top of the deep convection elements. Red is the control again. So for the most part, no surprise here, as I showed before, it's around 500, 600 millibars. But if you just include the kinetic energy piece, it's very deep all the time, which is probably unrealistic. It's not deep all the time. But the purple case, which includes both the parcel PBL property changes and the kinetic energy instrumentation, it has variation that looks realistic, I think. So, there are deeper periods, slightly shallower, the top set slightly shallower, during this somewhat dry period here in the middle, where it isn't raining in this purple case so much, then the convection is much shallower. But, just illustrates that, it seems to have more variation in the cloud top type, which is more, faithful to deep convective events and then essentially drier events. So that was just Toga core, and of course it doesn't convect just in the West Pacific and nowhere else. Another case, of course, is over the Central Plains, and this is a much more difficult case, which is unsurprising from a kinetic energy perspective. So on the left, that is just a repeat of these two kinetic energy experiments. But on the right is essentially if you do the same during, central Oklahoma, dry, storms, down the cycle period, I'll show you in a second. And so the critical thing here is the mean kinetic energy goes negative. And so negative kinetic energy was our criteria for the convection can go no higher. And so looking at the kinetic energy in this time frame for both the ARM-95 and Toga Core, we can see that it's a very different beast. On the bottom is Toga Core, which is much more smoothly varying. The cloud tops go slightly shallow, slightly deep. Boundary layer is pretty simple. But then obviously in the ARM case, white is kinetic energy going negative, which is essentially convective inhibition, or it's a very elevated surface convective layer. So it doesn't perform as well here, but we have one value for initial parcel and one value for the potential energy to kinetic energy conversion. So I think there's still work to be done. Oh yeah, and so there's different periods you can pick out here. So it's like done with a kind of mesospherical convective system type on the right here. So, and it makes sense, but it doesn't necessarily result in the best performing convection. And then finally, just to reiterate, these are at this point, these are fixed parameters that have, for Toga Core worked out to be pretty good. But you can see the sensitivity, for example, in the greens is if you change the efficiency of this P to KE up and down, and similarly the surface parcel properties up and down. And so, yeah, of course, the surface parcel changes. You start off, for example, in both cases, particularly ARM, you start off pretty energetic with the parcel. And so even this convective energy region that tends to negative convective inhibition that exists a lot of the time in the lower troposphere can be overcome with a stronger parcel initial kinetic energy. So I'm kind of in the middle of trying to tune this. So summary, this is the motivation for the vertical level potential sensitivities. And for the talk, implemented this very simple KE kinetic energy criteria for the plume viability. And then two simple parameters at this point. Performs pretty well for the tropics when it's combined with this PBL change. And but ARM, it needs more work. Next steps, CAM simulation, I've done some, and this translates to CAM simulations, and there are significant changes to the tropopause, which could be interesting with respect to some of our humidity problems in the lower stratosphere. And then, yeah, finally, I think the key thing I'm thinking about for the future, which makes a lot of sense, of course, is keying in this parcel initial energy to clubs TKE. That makes a lot of sense, particularly in regions with energetic boundary layers. Thanks.
Do we have any questions from the audience? Louisa?
I think I'd be very interesting to see what effect this will have on chemistry. So the lightning NOx emissions are tied to the top of the cloud top height, and also the distribution of tracers in the convective transport for those. So I'd like to help out in your next steps to run with CamChem to look at that.
Right.
Or maybe even ScamChem, look at your case and add chemistry with into
I mean, it is interesting, you get in the upper troposphere and it's the, is it non-local deep convection that plays the biggest part, which of course has an influence for transport, chemistry transport, water vapor transport versus a local club-based TKE, turbulence response. It is local, and so it's within an individual time set. This transport is not necessarily non-local.
So there's a different character of detrainment in your kinetic energy scheme. Is there just less moisture being pumped into the
By the time you get to the top, I think that's what's happening is because you've evacuated moisture, then the detrainment layer is not so dumping all the moisture it has out at that lower level. That's what I mean. I don't know for certain.
Yeah, it would be interesting to see that in the 3D model.
Right. In the 3D model, it's quite a bit drier in the free troposphere, but in the upper troposphere, it's moister.
Yeah, I'm kind of thinking of how much ZM is a gravity wave source. The detrainment layer is a huge gravity wave source to the dynamics that is drying out the stratosphere. So
Right.
If we can tame that down, we might help with the stratosphere bias, but there will be huge troposphere biases we have to tune again.
Have you thought about, how would this interact, or what would it look like if you coupled this with the improved convective microphysics that we saw earlier today? Would that amplify the heating that you're seeing?
I'm not know for sure. I mean, it's hard to know. I mean, the condensation is instantaneous, and so is the rainfall. In some fraction of it is instantaneous. So whether that delay, microphysical timescale delay, which is short, I don't know. Yeah, I mean, clearly did have an impact, but how that impacts with what the changes that I've made, I don't know.
Okay.
Thanks, Rich. I think the next talk is from Yucheng. It's remote. Yucheng, are you there?
Hi everyone. I was wondering if you could see my screen.
I think we can, but we don't see her. There we go.
Okay, thanks. Thanks a lot. So my name is Yu Chen. I'm currently a postdoc at Harvard working on boundary layer turbulence and land atmosphere interactions. My topic today is a logarithmic profile of temperature in shielded and unstable stratified atmospheric boundary layer. First, I would like to thank my co-authors, Chi, Dan, and Pierre. First, I would like to introduce the wall parameterization. As we know that von Karman's log law of the wall is one of the cornerstones of turbulence theory, and the log law of the wall suggests that the mean velocity is proportional to the logarithmic of the distance to the wall, where the distance to the wall is typically denoted by z. And then we can find that in this near wall velocity profile that the two layers, including the viscous sublayer and the buffer layer, are not resolved by large dissemination or climate models. Thus, a wall parameterization is used. And the von Karman log law of the wall is just can just be used as one of the wall parameterizations. And we note that in this type of universal log law, buoyancy effects are not considered. However, in an atmospheric boundary layer, a buoyancy effect can be very important. To address those buoyancy effects, Monte-Markov similarity theory uses dimensional analysis and assumes that the normalized temperature gradient is stability correction. And according to Monte-Markov similarity theory, the log law breaks down due to the buoyancy effects. However, Monte-Markov similarity theory cannot explain some important surface layer statistics such as the spectra of velocity and temperature. Recently, the logarithmic profile of temperature was reported in Rayner-Bernard convection. Thus, a temperature log law can exist in turbulent float driven both by shear and also buoyancy. So, and the goal of this study is to investigate the possible existence of a temperature log law in the atmospheric boundary layer driven both by shear and buoyancy. We conducted direct numeric simulations of the convective boundary layer ranging from weakly stable to high convective conditions. And then we use Zi over L to denote buoyancy effects. Zi is boundary layer height, L is covalence. And then in the neutral limit, Zi over L is 0. And then in the free convection limit, Zi over L approach minus infinity. And then we can find that in the least convective case, SH40, Zi over L is about minus 1.7. And in the highest convective case, Zi over L is approximately minus 10 to the 5. So here are the profiles of near wall temperatures. And then we focus on the black lines, which just denote the normalized temperature. And then the y-axis here just normalized temperature, and then the x-axis here are just distance to the wall in inner units. And then we can find that a linear relation can be a good fit between the normalized temperature and the logarithm of z, which is indicative of a log law. And we also note that the slope of this identified logarithmic profile changes from the least to convective case SG40 to SG2. This is in contrast to the universal slope of von Karman's log law, which is just 1 over kappa. In addition, we focus on this normalized heat flux, and we can find that those normalized heat flux are almost constant in the region where we observe a temperature log law. Thus, this region resembles the atmospheric surface layer where there are almost constant heat fluxes. To better indicate the existence of a temperature log law, we use a plateau of the normalized temperature gradient denoted by kappa z divided by theta star times d theta dz. And then according to those direct linear examination, we can find a plateau in this normalized temperature gradient. However, according to Molyneux-Markov similarity theory, this normalized temperature gradient is a function of z over L. Thus, it depends on z. And then which is clearly denoted by a slope in this plot. And we also find that for the least convective case, SH40, the range of the temperature log law resembles that of the neutral velocity log law. We also collaborate with field observations, and we use temperature measurements on a tower at range from 10 meters to 140 meters. And we can find that the normalized temperature can also fit a linear relationship with the logarithm of z, which is also indicated indicative of a log law. And then so why does the temperature log law not reported before? So there are possible two reasons. The first is that there are very sparse measurements in the vertical direction. Thus, it's very difficult to obtain a normalized temperature gradient in the atmospheric bound layer. In addition, there are large uncertainties in the measurements. And in addition, Molyneux-Markov similarity theory has been regarded as the fundamental theory of ABL turbulence. Thus, typically field observations are analyzed within the framework of Molyneux-Markov similarity theory. To identify the slope of the proposed temperature log law, we can conduct dimensional analysis. Fully developed convective bound layer flows can be described by nu, which is kinematic viscosity, Zi is bound layer height, Z is distance to the wall, theta star is the scaling temperature, U star is friction velocity. And then those variables can form three non-dimensional groups, Z over Zi and Zi over delta V, which is just the friction Reynolds number, and delta V is the viscous length, and Z over L. And so in the log law region, we can write the temperature gradient in this form. And if we further integrate this equation in Z from a reference height, and we can find the logarithmic profile. And we note that in this new temperature log profile, 1 over kappa theta is the new slope, and then it's a function of Z over delta V, denoting Reynolds number, and Z over L, denoting buoyancy effects. We also conduct asymptotic analysis for the slope of the temperature log law at sufficiently high Reynolds number. So in the neutral limit, theta star approaches 0 and Z over L approaches 0. And then this new temperature log profile, this new slope of the temperature log profile would approach a constant. And if we further assume that the turbulence prompt number is 1, then the slope would just be identical to the von Karman slope. And for the free convection limit, theta star approaches minus infinity, and the OL also approaches minus infinity. So for the existence of the formula, we have to cancel out theta star in this equation. Thus, we would find that kappa theta would be proportional. to minus z over L, meaning that as the buoyancy effects increases, the slope would further deviate from common constant. Here we compare the Money-Cope similarity theory and the proposed new temperature log law. So Money-Cope similarity theory assumes that the surface layer eddies are independent from eddies above, thus the normalized temperature gradient is just a function of the distance to the wall denoted determined by local eddies of height z. In comparison, we find that the surface layer eddies are influenced by non-local eddies above, meaning that the eddies of the scale of ABL height can penetrate into the surface layer and influence turbulence statistics. And then the normalized temperature gradient is influenced by non-local eddies of the height of boundary layer. To conclude, we propose a new temperature logarithmic profile in the convective boundary layer driven both by shear and buoyancy. And the slope is a function of Reynolds number and buoyancy effects. And then this should lead to physically based new temperature boundary condition in climate models. Thanks a lot.
Are there any questions in the audience? Oh, I apologize for the ignorant question in advance, but what implications does this have for a global climate model? Is this going to affect how surface heat fluxes are calculated? I'm not clear.
Oh, sorry, I didn't make it clear. So this should be used to compute the surface heat flux. So it's at the lowest grade. Currently, it's the surface heat flux is computed using Money-Cope similarity theory, which is actually been used in almost all the climate models. Right. And what we show here, there are some inherent deficits in Money-Cope similarity theory, and then the proposed temperature log profile might be used as an alternative to Money-Cope.
So will this in general reduce, if we have the same temperature at 60 meters, will your results reduce or increase heat flux? I guess I'm wondering if you have a sense for what change in the heat flux your new temperature profile parameterization would induce.
Yes, thanks. It's a great question. So as we showed here, so if you look at this figure, and then this is just the field observations of temperature, and then we can find the Money-Cope similarity theory systematic they underestimate this temperature gradient. Thus, it overestimates the temperature heat flux. Meaning, and then this overestimation of temperature heat flux by Money-Cope similarity theory further leads to the overestimation of temperature in highly convective conditions, for example, during heat waves. And then the newly proposed temperature logarithmic profile may partially resolve those overestimation of temperature in heat wave.
Okay. Thank you for that explanation. Yep, I think we're running a little late, so we're gonna move on to the next talk. But thank you very much for your presentation. Thank you. Our next talk is from Kyle Nardi. Parameterized momentum fluxes in club. Yeah. Let's try.
It's on. Okay, good.
2014. All right, excellent, thank you. Okay, so my name's Kyle. I'm a PhD student at Penn State working with Colin, and my PhD work is in support of the momentum flux CPT that Colin mentioned earlier today. And really the main goal of my work is to understand some parameter sensitivities within club and how that influences predictions of both extreme weather and also the global climate itself. So to put this presentation into context, we published a paper last year where we explored some club parameter sensitivities with respect to tropical cyclone forecasts in an idealized framework. And I'll just note here that we're using club with two modifications. So first, we're using the prognostic momentum flux formulation and also a regime-specific formulation for the inverse eddy turnover timescale. This is this TAUS formulation that Colin mentioned earlier. And what I wanted to point, and I also call this club X here just to differentiate it. And for all the results I'll show in this talk, I'll be using those two modifications. And the main finding, or one of the main findings from this paper was, by default, CAM6 with club has a lot of baseline biases in tropical cyclone structure. So the baseline time series of height of maximum wind and latent heat flux flaction are shown in blue here. And in comparison to CM1 in orange and NOAA dropsonde observations in gray, there are some significant biases by default in CAM6 with club. So what we did was we had a sensitivity analysis where we identified input parameters in club that have an appreciable influence on some of these output metrics. And if you want details about that, I'll point you to my paper, and I have a QR code at the end that goes into the details of the sensitivity analysis. But essentially, we get information about the magnitude of the response and also the direction of the response to changing some of these club input parameters. And we identified these influential input parameters and then ran some simulations with these perturbations with the idea of reducing some of these biases. And the range of the time series from those simulations is shown in green. And what we found is that with some of these parameter perturbations, we can reduce some of these biases in tropical cyclone structure. So sort of the follow-up question and what I'll be presenting here is trying to answer the question of how can we assess whether or not some of these input parameters are influential for tropical cyclones are also influential for the rest of the global climate? Because ideally, we don't want to make changes to improve tropical cyclones, but then also make the rest of the global climate worse. So the main goal of this talk here is to sort of start to examine some of these sensitivities with respect to the global mean climate. So we'll look at several different baseline biases in CAM6 with Club X. So this is from a 10-year simulation with baseline Club X parameter settings. So I'll point out the Southern Ocean here. Baseline surface stress is too high. So that's one potential region we can explore for some of these parameter sensitivities. And then also we'll look at shortwave cloud forcing biases in the central and eastern tropical Pacific. And this is due to high bias and low cloud fraction using these baseline Club X parameter settings. So we're going to go in and do a similar sensitivity analysis where we now ask the question, do those input parameters that influence tropical cyclones also influence some of the environmental conditions that are giving rise to some of these biases in CAM6 with Club X? So there's a lot to show here with this plot, but essentially we're looking at here the direction of the response when we change one of the particular input parameters on the horizontal axis. In what direction are we moving some of these outputs? So we have different fields here. So we have wind speed, so this is magnitude, at the bottom model level, and then at several levels above that, and then surface stress is up at the top. So the way to interpret this is for values that are closer to 1 in the dark blues, that implies that increasing the input parameter frequently increases the output. And then values closer to 0 in the reds implies that increasing the input parameter frequently decreases the output. So we're looking for dark blues or dark reds, essentially. That's giving us confidence that when we change these input parameters, we're going to get a consistent directional response over the Southern Ocean, area averaged. So I'll highlight these two input parameters, C inverse tau shear and CUU shear. They're both related to governing momentum flux or vertical turbulent mixing in the presence of high vertical wind shear. And what you can see here is that when we increase these two input parameters, we're getting a consistent decrease in the wind speed at the lowest model level and an increase in wind speeds above, which is essentially resulting in an increase in vertical wind shear. And we're getting a reduction in the surface stress when we increase both of those input parameters. We can also look at some cloud radiative fields over the tropical, eastern, and central Pacific. And we see several other input parameters that are influential for low cloud fraction and shortwave cloud forcing. One of them I'll point out is the gamma coefficient, which has been shown in other studies to be influential for low cloud fraction. When we increase gamma coefficient, we're frequently decreasing low cloud fraction, and we're also having a change in shortwave cloud forcing. And what I want to note here, to answer the question I posed in the previous slide, these input parameters were also influential for tropical cyclones, meaning that when we make changes to improve tropical cyclones, we're also going to be having an effect on some of these regional biases in a global simulation. So that's something that will give us a little bit of pause when we're making some of these parameter perturbations. So, and I also should point out here that these are all from 3-day initialized hindcasts, similar to the construct that Colin mentioned earlier. So that allowed us to essentially perform more simulations with less computational cost. But what we wanted to do now is test some of these parameter perturbations for a 10-year simulation. So a similar 10-year simulation as what I showed before, but now we're going to make perturbations to those 4 highlighted input parameters, and we're changing those parameters based on the directional responses I showed in the previous slide. So I'm comparing the output from this perturbed 10-year simulation to the baseline 10-year simulation. And we can see that we do get a reduction in surface stress over the Southern Ocean region, which was predicted by the sensitivity analysis. And we're also getting a change in the shortwave cloud forcing, and this is due to a reduction in low clouds, which was also predicted by the sensitivity analysis. So there are a couple of questions that you could ask to follow up from this. So first is, how do we address the effects seen in other regions? So I was looking at the Southern Ocean or the tropical Pacific. We had changes in those regions, but there were a lot of reds and blues elsewhere. And this will certainly be a question my PhD committee asks. So it's something that I will be considering. That's more future work, so I don't want to talk about that quite yet here. What I do want to address, though, is some of the physical mechanisms driving these sensitivities. I don't want this to be a purely tuning exercise. I want to be able to sort of use these sensitivities and reduce model biases, but also understand why we're reducing the model biases and making sure that we're actually producing a physically realistic profile of turbulence in the boundary layer. So I'll just put up here the club prognostic momentum flux formulation. And a lot of terms here, and there are a lot of tunable terms. So pressure terms 1 through 4, all of these C coefficients that are tunable within club. And we're actually directly affecting 2 of these terms. So this inverse tau here, that's one of the parameters we found to be highly influential, or a component of inverse tau. So we're going to be directly affecting that, and also that 1C7 term there in pressure term 4. But we're also potentially indirectly affecting a lot of these other all these other terms through modifications to the environment, like for instance wind shear. So we want to do an analysis of how changing these parameters influencing all of these terms here in the momentum flux budget. And then quickly I'll just go through this inverse tau formulation, and has these different terms here that relates inverse tau to turbulent length scale, but also inverse tau is the sum of these 4 eddy dissipating processes: background dissipation, dissipation due to surface friction, wind shear, and stable stratification. And one of the input parameters we're changing in this multi-perturbation simulation is this C inverse tau shear, which is going to weight the eddy dissipation in the presence of high vertical wind shear. So I'll show here momentum flux budgets, and hopefully the changes here are subtle. So the dashed lines are the vertical profiles of the momentum flux budget terms in the perturbed simulation. Solid is in the baseline simulation. And I want to point out several of these terms. A couple stand out as being higher magnitude than others. So in green is the turbulence production term. So we see an increase in the magnitude of that term when we make some of these perturbations. In lavender, which might be a little hard to see on the screen, that is pressure term 4, which is essentially opposing the turbulent production. And we directly change that input parameter C7. And this term also increases in magnitude. And then we have this pressure term 1, which is a return to isotropy term that has that inverse tau in it. And we're specifically increasing inverse tau But we're not getting very much of a change in the pressure term 1 itself, which I'll talk about in a second. So I broke inverse tau down into the 4 different dissipating terms. In red is the dissipation due to vertical wind shear. That's the term where we increased the coefficient in front of it. So as we would expect, we're getting an increase in that eddy dissipation. And then the totals in yellow, we're getting an increase in the total inverse tau. So we expect this first term here, C6 over tau, C6 is constant. That first term there is going to be increasing. We also see we get an increase in vertical wind shear, which was anticipated by the sensitivity analysis. And that's interesting because that du bar dz is appearing in pressure term 4 and also in turbulent production term. So due to the change in vertical wind shear, that could be influencing the momentum flux budget term there. And then we're also getting an a decrease in the magnitude of the momentum flux. And what we hypothesize is happening is the reduction in the momentum flux is not allowing as much of an efficient distribution of winds, where we're not bringing down the stronger winds aloft as efficiently down to the surface, and that could be one cause of this change in vertical wind shear. But what I want to point out here is that a lot of these different environmental metrics are going back into these budget terms. So even though we're only changing a handful of these tunable parameters, we're also making changes to the environment, and that's feeding back then into these budget terms. So just to say that there's a lot to tease out with some of these terms, and trying to understand exactly what's causing what is something that is an ongoing challenge for us. We're trying to understand better. So this is the last result slide. So now we can do something similar for scalar fluxes. This is heat flux theta L prime, W prime. And we can also point out turbulent production here now that has the d theta L bar dz term. That is changing, and also the return to isotropy term is changing as well. That has the scalar flux in it. And we're seeing a change in the stability profile, so the change in Brundt-Väisälä frequency, which you can kind of see the shape is sort of shape of the perturbed profile is sort of matching what we see with the turbulent production term. And then we're also changing heat flux itself, which is going to then affect pressure term 1. And there's a pretty good comparison between heat flux and then this profile here for pressure term 1. So I'll put my main takeaways here. And what I really just want to highlight for future work is, so we can see that these perturbations are changing the profiles. But one thing that's missing is sort of comparing these profiles in CAM6 with Club X to observations. And these are data sparse observation areas in terms of momentum flux in some cases. So we're thinking potentially we can leverage a high resolution model like CM1, potentially at large eddy simulation scales, to be a proxy for observations. I know George Bryan has put Club into CM1. So potentially working with him to get some of these club metrics at a finer resolution, but also just using CM1 to give us a better sense of what these profiles actually should look like. I think would be very helpful. And also, I'll just mention too, trying to understand how we can better contain some of these effects to certain regions of interest. And we hope the TAUS formulation could be one way to do that. Yeah, so I'll just leave my info up here. I don't know if there's time for questions, but if there are, I can answer any. Or you can contact me here.
Yeah, I think we should take a quick question. Ben?
I just had a simple question.
Yeah.
When you said you were changing C7, are you actually changing CUU shear?
Yeah, so I didn't want to sort of go down that rabbit hole, but yeah, that formulation there, it's kind of, C7's been kind of split now. So I'm specifically looking at that pressure term 4, which is the CUU shear now, which is related to the vertical wind shear. Yeah, so it's a good question.
Yeah, I had split it up, so I was wondering if.
Yeah.
All right, thanks, Kyle. I think, yeah, we will move on to the last talk of the session. Well, actually, the last talk of the meeting. So, it'll be from Joaquin Pico. Also on flow momentum.
So let's see if we can do this. So we did something like that, but I named it like C7WP.
Just hold on. Okay. Yep. Perfect. Okay. Hi, everyone. A pleasure to be here at NCAR to present some results that I've been working on. So my name is Joachim Pycke, and I'm a PhD student at the Department of Meteorology at Stockholm University. And the topic of my talk today is evaluating low-level jets and boundary layer processes in CAM6 runs nudged using ERA 5. So just quick background on where I work. So I'm part of the Momentum CPT that Colin and Kyle mentioned earlier, and which essentially works on improving momentum fluxes in the club scheme, including myself, and my supervisor, Professor Gunilla Svensson, who is also here in this room. So a little bit of a motivation on why I'm showing you the results I'm going to show you today. So during my PhD studies, I have had an interest in processes that describe the behavior of the boundary layers, such as the wind turning over the boundary layer and the cross-isobaric mass fluxes in the boundary layer. And I have a paper on the wind turning in the planetary boundary layer in CMEP6, which is submitted. And this is one of the main results in that study, which shows the probability density functions of wind turning angles over the boundary layer for different CMEP6 models, ERA interim reanalysis, and the observations in the black dashed line. And we found there, for example, that we had a general underestimation of wind turning angles in CMEP6. But I also have a role in the CPT to evaluate different boundary layer processes, and what I usually look at is vertical profiles and low-level jets. So that's what I want to get into right now. So today I'm going to talk about CAM6 runs that are nudged using ERA 5. And so these runs are nudged using ERA 5 above certain pressure levels. These are typically at levels that are meant to be somewhere above the boundary layer. So if we look at, for example, these potential temperature profiles here, we typically expect the nudging to occur somewhere above in this upper part or above in that plot. But the nudging we nudge the temperature and the winds, and we use 32 and 58 vertical levels. And we have a specific focus on the Southern Great Plains arm site because there's a plethora of observations to use there as well. The period in focus here is between 2018 and 2020. So one thing to look at first is to look at whether or not the weather matches the nudged run, the weather in the ERA 5 or observations rather match the nudged runs. And so, sorry, we don't have free runs in this plot, but we do have two nudged runs in this plot showing 32 and 58 vertical levels in blue and red respectively, and compared to observations in black. So this is surface pressure time series throughout 2018. What we see is that we have that CAM6 follows the observations pretty well, although there are some differences, especially during the middle of these periods. But what we can say from this is that the observations can still be used to compare with the nudged runs in terms of the weather actually matching. So I also looked at the geostrophic wind speeds in the different nudged runs compared to observations. So we have here the PDFs of geostrophic winds compared to observations in black and ERA 5 in the black dashed lines. And we have also that the geostrophic wind speeds here is defined as the wind speeds directly above the boundary layer. So what we see here from these PDFs is that all of the runs, even the free runs without the nudging, have geostrophic winds that are higher than the observations in ERA 5. So the reason for that is because the boundary layer heights are found using the Bolk-Richardson method, which I'll show you later will actually have a bit of an effect on sort of where we find the boundary layer compared to in the model compared to the observations. So this could be possibly one of the explanations why we have this difference. But so Also looked at low-level jets in the CAM6 nudged runs compared to free runs and the observations. So these are this plot here shows the PDFs of low-level jet wind speeds, which is the wind speeds of the jet maxima for two different nudged runs using 32 and 58 vertical levels and both are nudged close to around 690 hectopascals, so typically above the boundary layer. And then we have two free running models, and then we have the observations in Aero 5 again. And what we see is that we have generally higher wind speeds in the model runs compared to observations and the reanalysis. But when we nudge, it seems that the wind speeds do tend to be a bit lower, so that they become a bit closer to the observations. And one thing that I don't show here is also that we found that we typically have higher or larger low-level jet heights, so that the jet is found at a higher elevation. So we wanted to figure out why is that. So we've thought of looking at how the evolution of the boundary layer before a low-level jet event looks like. So what we did was we took one particular case. So this is a case from the 9th of July, 2018. So we have, what I plot here is just, for this case, the boundary layer height time series before the low-level jet event that happens in the latter part of this plot. And we have the boundary layer heights from Era 5, and the observations are just from radiosonde data. That's why we only have the observations 4 times a day. But also, we can see that this is from the nudged runs, we see that this is a dry convective boundary layer case. So we have low boundary layer heights during the night, and then we have high boundary layer heights during the day, as we'd expect. But if we compare what we see in the observations in Era 5 to the nudge runs, we see something different. We see that we have high boundary layer heights during the night, and we have low boundary layer heights during the day. And so here, again, like I mentioned, the boundary layer heights are found through the critical bulk Richardson number method. So I would like to quickly just explain what is that. Well, we just, at this location, we calculate the Richardson number. So we use the UMV wind components, the temperatures, the specific humidities, and the pressure surface pressures to calculate the Richardson number at each model level. And then we find the first model level that's where the Richardson number exceeds a critical value of 0.25. And we set it to 0.25 because that's motivated from previous studies. And then we also do a linear interpolation to find an estimate for the boundary layer heights. This method is widely used, especially when compared to observations. So this is one of the most widely used methods for finding boundary layer heights, especially if you only have the mean fields. So what I did then was to take a look at vertical profiles of different variables for this particular case to see to study like the effects of, or rather to study what is going on with the boundary layer heights in the nudged runs. So these are 6 different panels. So we have potential temperature, we have specific humidity, wind speeds, momentum fluxes, heat fluxes, and wind directions for the different ones. And we do see, in this case, I only added one of the nudged runs because, as you could see from the previous plot, the nudge runs seem to behave pretty similarly. So if you look at the upper left plot, which is the potential temperature profiles, so the nudged run is shown in red, magenta, and blue. Those are for 3 different time steps. It's for 12, 15, and 18, so noon, 3 p.m., 6 p.m. And we have the observations in the black lines and the Era 5 in the black dashed lines. And we could see here that if we look at the potential temperature profiles in the the model runs, we have, whoops, I must have gone forward. There we go. We have that the potential temperature profiles are way too stable compared to like the observations in Era 5. And in fact, oh, I did it again. And in fact, we also have these yellow stars indicate where we find the boundary layer heights using the Bulk-Richardson number method for both the model runs here. And then it's not as clear, but we also have black stars up here showing where we find it. Oh, that's a bit too sensitive, this. Where we find the boundary layer heights in the observations. So we find boundary layer heights in the model runs below 500 meters, while in the observations we find boundary layer heights at about 2,000 meters. So there's quite a bit of a difference. And if we look at, for example, the profiles of the specific humidity and the wind speed and the wind direction, we see that we have a pretty well mixed case, even in the model run. And in fact, for the specific humidity, it's pretty dry compared to the observations in Era 5. So we have a very stable potential temperature profile, but it still seems to be well mixed. And that's because if we look at the momentum fluxes in the lower left and the heat fluxes in the bottom middle here, we actually have turbulent fluxes. If you look at momentum fluxes, we have turbulent fluxes up until around 3,000 meters, and the heat flux is up to until about 2,000 meters. So if we, for example, use the boundary or the heat fluxes to calculate the boundary layer height, so we find the height of the minimum heat flux here, we see that if we plot that as these yellow dots on the potential temperature profiles, we see that we get something that starts off as just above 1,000 meters, but goes up to over 2,000 meters, which is a lot closer to what the observations show. And so, yeah, we find way too low boundary layer heights using the Bulk-Richardson number method with these profiles. And we also wanted to look at, well, what does this look like for, so this was a run with 32 vertical levels, so does it make a difference if we use 58 vertical levels? And that's what I kept going back to here, which was it's the exact same thing, but for a run with 58 vertical levels. And we can see here that we have a very, very similar case. We have boundary layer heights using the Bulk-Richardson number method for around 500 meters. And then if we instead look at the heat fluxes, we have somewhere above around like 1,200 or 1,300 meters and up till about 2,000 meters. And again, a pretty well mixed case as well. And we have momentum fluxes up until about 2,500 meters. So it's still very much a similar case for a run with a higher vertical resolution. So one last thing I wanted to look at was just to see, okay, well, is this just the case in the nudged runs, or is it a similar case for the model itself when it's not being nudged using Era 5? I have plotted here the boundary layer height PDFs for 2 different runs. So it's one nudged run and one free run for 3 different methods. So the Bulk-Richardson number method is shown in the pink for the nudged run and in cyan for the free run. And then we have using the heat fluxes for the red and blue lines, and the dark red and dark blue for the, if we use let's take a look at the momentum fluxes. So this is a little bit messy, but one general thing we see here is that they end up being very similar. There's a bit of a difference between the 2 runs for the heat flux method, but still, generally speaking, they are very similar, which means that it seems like the nudging does not really tend to mess up the boundary layer structure. So some summaries and some speculations and future work. so the nudging, like I said, does not seem to ruin the boundary layer structure. But we do have too much stability during convective cases, because the case that I showed here, we've seen in several other cases as well. So during the convective cases, we have too low boundary layer heights. During the daytime, using the bulk Richardson number method. And one possible reason for this could be too much subsidence, which we also want to look into further. So we also found too large low-level jet heights, and this could be due to the way that the boundary layer behaves in the nudge runs. And also, what I would like to do from now is to continue analyzing low-level jets, knowing that we have this type of boundary layer evolution, and see what we can find out more. And also, we're going to set up a single column model case for this, and sort of change the vertical winds to see how much the vertical winds have an effect on the stability that we see in the nudge runs. So thank you for your attention.
Thanks, you're welcome. Brian, I guess one simple question is there did you test for sensitivity to your threshold, your 1/4 value for the bulk Richardson number? Does that make any difference?
No, I didn't do any sensitivity tests for the bulk Richardson number. I have mostly just used motivated my choice of 0.25 using a previous study that actually looked into the sensitivity of this, and they found that that's a pretty good value. So, yeah.
Have you looked at precipitation over?
I haven't had time to.
Okay, yeah,
I'll
no,
look
that's-
into that. Yeah.
Oh, thank you. Do you want to
ask one last
quick
question?
question?
I guess. Were my eyes deceiving me, or were the 58 level model? It did look like those profiles were more vertical, and you did have some improvement in that as a function of vertical resolution. Is that your interpretation as well?
Yeah, I should have mentioned that actually. It's true. They are a little bit more vertical compared to the 32 level one, but you still find the boundary layer height at still.
Well, they're still clearly stable.
Yeah, exactly. Still fairly stable. Yeah.
All right, I don't think there are any questions online. So why don't we take a 10-minute break, or, come back at 20 minutes to 3. We'll have a 20-minute discussion, and that will be it for the meeting. All right, thank you very much.
point.
Oh.
He does this to me, he's like, wait, I'm like, I'm already coming.
You're not. I'm trying to get it
I'm trying to
You have to just go all the way back around again.
All right, so I think we'll just go ahead and launch in.
This is where I sit.
So, Wayne pointed out, you know, that it's good to be clear about the timeline, and so I'm repeating this. So we expect CAM 6++ to be ready sometime in 2024. So not tomorrow or next month, but for all practical purposes, when it comes to tuning a couple model, pretty soon. And so the corollary of that, as Wade pointed out, is that, you know, we're kind of close to the runway in terms of model physics. You know, if we find a problem, we'll turn around and, you know, do something, but we're not putting new parts or unfamiliar parts on the airplane at this point. So we have this list of physics, and, you know, going from what we're very, very confident will be part of CAM 6++, more or less to what we, you know, hope with some, you know, reasonable optimism will be part of 6++. So that raises the question, you know, for the community. This is a community model, and, you know, I'm sorry to have presented it kind of that, you know, we're sort of a closed shell at this point. And I would say that, you know, maybe for CAM 7, that is sort of the case, but we're you know, this CAM 7 is not the last version of CAM. And the community can also contribute to evaluation and tuning, I hope. And there have been physics development mentioned. There have been elements of, you know, new physics that we probably should consider soon for the model, including convective microphysics, CERS, and then there were a number of talks that mentioned machine learning-based replacements for things. And, you know, other topics that came up during the meeting, and I'm hoping that you guys will, you know, if you have the energy, contribute. We talked a lot about variable resolution configurations, and Patrick, I think, mentioned that we need a better, maybe a better strategy for curating these regionally refined configurations. How are we validating them, et cetera. And there were also 2 talks yesterday that, you know, highlighted real problems maybe with CAM 6 physics as we approach really high resolutions of 1 kilometer. So those are things I thought, you know, we could talk about. So I'm now opening it up to input from people here and people online.
See the chat window and.
I think Ray is,
Kevin,
oh,
there
good, that's
it is.
good, thank you. So Leo and Kevin have raised their hands. Leo's first, I think, according to Google. So,
Okay, thanks. We always trust Google. Yeah. Okay. So Julio, I just wanted to make a couple of comments. So I thought there were some very striking results presented. They maybe won't make it to the 2024 model, but I think especially the convective microphysics, I've actually thought this has been important for a long time. The earlier Song and Zhang work was already fairly compelling. What we saw today, I thought made it much more so. So that's something that maybe we at least ought to elevate as coming in next generation. I even maybe wonder if it can go in the faint blue along with EDMF if results look promising on it. The other thing I thought was very striking, not so much because it's just machine learning, But I think what Andrew showed about the warm rain process simulated by machine learning looks a lot different from the parametric approaches we've used in the past. So if we can't get that in yet in Pumas, it needs to, I think, be something that surfaces maybe fairly soon. This is really, I think, important physics, and there's really nice progress being made on some of those things. So those would be the comments. The other thing I wanted to just mention in connection with it, it sort of goes to the second talk from Rich. And to do some of this microphysics in convection, we actually need vertical velocities. And so you could probably back that out from the kinetic energy that Rich is talking about, or of course it's in the EDMF plumes from the CPT. In fact, it would be very interesting to look at the vertical velocities that come out of the two strategies. Song and Zhang had to kind of back out some vertical velocities in the convection plumes because it doesn't automatically come out of conventional Zhang-McFarlane. So I think that that's important. And I'll just mention with one last gasp, there are now observations that can be used with single column models coming out of ARM to actually look at vertical velocities in deep convection, Doppler radar, sounders, and so forth. So we have a way of actually checking out some of the things like the KE and the vertical velocities. It will be important to coherent representation of convective microphysics or better warm rain microphysics in the deep convection using the ML, and of course the ML for stratiform too. So sorry that we're so many things there, but it's been a great meeting and some very interesting things that I think are really worth bringing into this sooner, if not later.
Right. I think the convective microphysics is interesting. It's also, I think, a little complicated. Do we focus on ZM for this, or do we, go to the MF plumes?
What's currently in MF from a microphysical perspective?
I think it's still pretty simple microphysics in the MF plume,
Real
right?
simple.
Yeah, definitely. There are papers out there. They're older Song Zhang implementations but it was moved forward a lot today. I think so the packages are out there, but it's extremely simple at the present time. And this has been, I can remember GCSS meetings 20 or 25 years ago when GCMers were, you've got to do something better in the convection to make it more like the stratiform. But groups have been slow to do it. It's been a tough problem. And it does get mediated by those convective vertical velocities, which the older mass flux schemes didn't have.
Well, thanks, Leo. Kevin, you wanna?
Yeah, so I had just a maybe it's a comment, but more of something that I think we should think about outside of the meeting, which is, from my observation over the last 3 days, I think we saw a lot about the development that's going into the workhorse, kind of model for CAM 7 and potentially down to CAM 8. But one of the things that I was maybe, struck me the most compared to past working group meetings is that, there is now a lot more flexibility in how people are running the model, right? So a lot of what the work that's gone is, to make variable resolution a little bit more configurable for individual needs. And we saw that both with, some results with SE, but also with results with MPAS. And we're seeing now that it's easier for people to start, especially once CCPP is instituted, it's going to be easier for user choices of different parameterizations to use. Of course, there'll be the workhorse configuration, but what we're seeing, I think, in my viewpoint, is a transition to a lot more like how things were done traditionally in WRF, right? And that a user can configure their domain and they can configure their parameterizations for their need. And I think that's great because it does provide a lot of flexibility for different scientific questions to be looked at. But it related to the kind of second 2 lines here, evaluation and tuning, I don't think there's a clear, I think we saw a little bit with some of the tuning talks, but I think we need to come up with a better community approach or a standards approach to how, when you've configured your model with a certain variable resolution,
right.
Or if you're going to use, some of the CAM 6 physics, but you're going to change the club, a little bit. I think we need to have a way that's kind of community accepted of how we're at least doing some high level tuning of the model, or else it's going to make it really hard to compare against studies or to understand where real benefits are coming from and to inform future development. So I don't know. It's more of a comment of, I think tuning has always been the elephant in the room, and I think actually over time it's just become a bigger and bigger elephant that's just eating more and more, and we're pretending like it's not there. And so I think that that's at least something that we should think about, and maybe it's more than just AMWG. But also one of the other things that struck me was actually with the variable resolution setup is that, we see some of these results that are focused on the phenomena of interest, whether it's a supercell or a front or a tropical cyclone. And a few people ask questions about this, but then we're forgetting about what's happening on the other side of the world at the low resolution. Right. And so another elephant in the room that we haven't really addressed in the last decade still revolves around the scale awareness of these parameterizations. And I think that's kind of is related to the tuning to some extent, but I just wanted to bring that up as something that I see as an area of opportunity to potentially maybe focus on it as a community in the coming years.
And I think the variable resolution sensitivity is related to our time step sensitivity because we have to, it's slave to the high resolution domain. But Colin.
Yeah, well, I mean, I was gonna say this, but it follows up very nicely from Kevin's Kevin's comments is on your next slide, Julio. I mean, I feel I've been saying this for 10 years, but this idea of the variable resolution configurations. And, previously I would argue it was more difficult for a user to apply variable resolution, which wasn't necessarily by design, but it wasn't also necessarily a terrible thing, that they kind of were working with someone here, whether that be someone like me or someone like Adam. Right. And there was confidence that grids were well posed, that files were generated correctly. And I do think that we're pretty close to a point where we're going to have to make a decision as to how free we want these tools and the configuration to be. I mean, bringing up the WRF analogy, WRF is great. It's extremely flexible. You could generate whatever domain you want. You could run whatever physics you want. If you gave truth serum to some people down in M-cubed, they would say at times that has been a very big problem, where people have generated a domain and run a boundary layer developed for Arctic meteorology for a hurricane simulation and then published it in Nature. I don't know what the right answer is, but I do think that's something we should think about, and we don't want to just throw these tools to the community and say, look how easy it is, go run it. But on the flip side, it's also not, we want people to be using those configurations. So I don't know what the answer is, but I think that dialogue is coming fast, so.
I would just say that this is an opportunity to investigate ways that you can have better transparency about the adequacy of different configurations and different features of the tools for answering different sorts of questions, and think about how to go about having explicit and standardized documentation for that kind of thing. And with, what Simone was talking about, right, having those kind of variable resolution, like almost a repository or something, figuring out how to kind of make those available, but kind of provide some kind of guidance on adequate uses or appropriate uses versus things that you absolutely ought not be doing with these types of things. Just some kind of guidance documents. It doesn't even have to be anything like super comprehensive. You can go back and you can look at kind of what they've done in other model-based sciences where they've shared out various models or configurations and adapt some sort of those practices, or even look at like what Clara Desser's group did with the large ensemble simulations to at least provide some caveats, right? So that people can better understand what they're doing with the model and what type of inferences they can make from their use of the model.
Should this be part of CEMA? Since CEMA is very involved with variable resolution, should part of CEMA be a communication effort?
Good luck getting, good luck.
All right.
Go ahead, Jesse.
Sure, SEMA could be whatever you want at this point, I feel, so, But, yeah, Adam should go, yeah.
Well, I mean, so right now, in order to have some control that people aren't running grids that we don't approve of, the one approach that I've been taking is putting supported, right now you can run 3 grids out of the box if you check out CESM. You can run CONUS, Arctic, or Greenland grids. And I have those grids have been vetted, obviously. I have them configured so they're running a small physics time step. In the future, I may outfit one of them with some preferential tunings. But in terms of controlling what the community is using, I think that would be the way you can control it the best, would be we support these grids and they're, they have our stamp of approval.
Right.
You can run them.
And everything else is caveat emptor,
And everything else is what?
buyer beware.
Yeah. Then there's the second effort where we have actually worked hard to make it so that users could make their own grid, and they could run it with CSM without even having to touch the source code. And it's made it a lot easier to run grids. And so, I've made documentation saying that this is how you need to set up your time stepping. And Patrick has extensive documentation about, don't make your grid bad, but that's all, a lot of the people who have worked with those user-defined grids I ask them if they read the document, and they're like, well, I started, but I didn't understand it.
Right.
I'm like,
Documentation it requires a lot of work both on the production end and on the, on the reading end.
We need translators.
Well, it's worth mentioning there hasn't been formal CAM 6 documentation, right? At least that I'm aware of. So it seems that we've, as a community, gotten off the boat of documenting in detail the decisions that went into the current model version. And I think that's okay because the model versions are iterating so probably a little bit more frequently than they have in the past. But I do think there needs to be some type of way to, whether it's like some type of walkthrough of pipeline, right? So you're going to start to run stuff and I don't know, it's almost could like, how do you build it and what are the caveats and where could you click on an example? Okay, other people have done variable resolutions for the North Atlantic mesh. And when they did it, they used X and here's the paper, for example, to look at it. And I think the other thing to help around this is to realize that oftentimes when people are coming to use the model for a specific science application, which is a majority of our university users, right, is they actually aren't looking to reinvent the wheel. They're just looking to find what are the other ways that others have done it, because they would just match that if it's more easily accessible to them. And so I think that just having a place where you could document even, right, when you submit a paper, you could say, okay, here's the comp set and here's the, here's the blah, blah, blahs that I pulled together through CCPP or whatever. And it could be just a way for other people to replicate by actually using those kind of run cases. Could be another way to help around it. I don't know.
I think Lisa and Jesse had comments.
Yeah, I was just gonna say, we've been trying to provide, we as part of the Musica page and for chemistry people, a list of available grids or grids that people are developing. And we have, Adam and pointing to Adam and Patrick's documentation. But maybe the next step is to help provide some guidelines on what exactly should you look at in your simulation. I think we should continue to encourage people to make their own grid for their own application, but maybe we can help provide, okay, before you start running all the chemistry, make sure X, Y, Z look good in just the dynamics and the meteorology.
Almost like a checklist to
Right.
make sure that you have something that's adequate.
Right.
Yeah.
And some.
It's a great idea.
diagnostics, help, as part of the diagnostic package, something that can read a variable resolution grid and make sure the precipitation looks okay or whatever.
I see Simone had put a link in the chat.
Yeah, that's to our wiki page.
Well, I was gonna give an actual serious answer to the points that, Monica and Lisa just brought up and others, thanks, if you do want, if we want to provide like a basic, like, this is what, the physics packages say is for, maybe we could make that a requirement before a physics package is accepted into like the repo, right? We could say like, you have to provide, the software engineer shouldn't check the validity of that, but at least we can force the requirement that like, you need to have some sort of guidance into what this physics package is. And in the most extreme example, we could even put it in the code where, like, we talk about scaleware parameterizations. If you knew that this physics package didn't work below a certain resolution, we could put that in the model. So if you tried to run at like 10th of a degree resolution and this physics package isn't good for that, the model will just, you should always have an override, but you could have it like, by default, it just fails, right? It says like, no, I won't accept this combination by default. And so,
I mean, the groups working with MPAS at 3 kilometers have obviously, been tweaking.
well, yeah, and like, of course, and people are gonna do science, so you want ability, it's basically like the run unsupported flag that we have in CESM. I mean, a lot of people just add that all the time, so it doesn't do its job, but at least it puts some barrier where it says like, you should at least think about this before you do it, so.
I mean, it's making transparent information that they might not otherwise like consider or wanna dig for, so that at least it's out there. And they have more information to make a decision. The problem now is that like, you can't normally find that type of information if you need it. Like, there's no like documentation procedures or anything like that, and so you can take the time to ask an expert, right? But a lot of times, I mean, because the people that are supporting the community are spread so thin already, like, you can't give that type of attention to everybody that might want that information, or they can't understand it when they read it.
Right, yeah, well, that's why, I mean, cause what we could do, we kinda do this already with some documentation, is that's why you could make it a requirement for adding code in, cause then you basically have an automatic system that'll just take, there'd be like details, but essentially, we'd have some form, and then the people would fill out the form, and then we would have scripts that would automatically just put it onto some website or something, and then that would be where, at least it would make it a centralized place, and it would minimize the amount of effort of, contacting people to know, you could at least give you a first stop to look up some of this stuff.
Yeah, and it's all there, you're directed towards it, like, it's all in a singular place, so you don't have to like, go searching for all the information. I mean, it's a great idea.
Thanks, but
We do have a CAM 6.3 users guide, by the way.
Right, that's another good question is what, Kevin mentioned the documentation. What is the best form of for documentation?
Is that a tech report? Or is it a? Oh, it's just
No, it's a
online,
tech
like
report.
GitHub or something? Okay.
And you can get to it from a wiki, from the Git CAM.
Oh,
site.
yeah, okay.
But that Kevin didn't know he had it means that we did not.
Well, no, I'm talking about, so there's a difference between the user guide and the actual formal written documentation of what are the schemes in the model, right? That doesn't exist, or maybe I'm wrong, but.
Yeah, it doesn't exist. We don't have something.
So that hasn't, and so that's what I'm referring to, right? Is that we kind of default to assume that the community is going to go off and find the right papers on the parameterizations to read. I mean, I think that, and that even doing so, it wouldn't be correct because a lot of modifications happen to those parameterizations and they're built into the model. And I still go back to the CAM 4 and CAM 5 documentation all the time when I'm thinking through things. And so I think it's actually kind of to some extent a loss on the community that we don't have a CAM 6 documentation.
So you're
And that's something we should.
You're talking about the CAM 4, CAM 5 technical reports that are.
Yes, the ones that actually document, right, the dynamical core that's in there, any updates that have been made to it, the ones that document, right, the actual parameterizations, the actual surface schemes and all that.
There was one for.
So one option I would propose on this, and I agree with Kevin, is we do actually have a fairly distributed network in CAM 6 about you know, like Peter had his paper in James with the new SE core. At the very least, the lowest hanging fruit is, as a community, or at least the developers, can put together some of that documentation in a central location. So even if we don't want to go through, I think Rich was the one that was technically the lead author on the CAM5 tech report. I don't know how much effort it was. It was a great resource, but it's many pages of, you know, but at the very least, like if I'm using SE and I want to know something about SE, like I'm not trying to like scramble through Google Scholar, but I go to the AMWG website, I click on Peter's awesome James paper, and boom, there we go. And I do think that is missing somewhat, so.
But you need something more dynamic, because we've made changes to the SC core since that paper.
So it's an FTE problem, you know, like, who's gonna spend the time documenting? But at the very least, you know, it's kind of the same thing with the new parameterization going in. Most of these parameterizations have publications tied to them. You know, I don't know, that's a thought. I mean, it'd be great if we could have 600-page tech notes. I don't know who's gonna write it, so.
Yeah, I mean, we have to be realistic. I mean, other equivalent modeling centers like the Met Office have probably 100 people that work on development and writing reports and stuff. And like, we would love to be at that level. And everything that's been described now is kind of hoping to be at that level, and we just can't do it. I mean, it's one of those problems where we have to reach out to the community, but then
I mean, can't you
they're
start
over.
something and get buy-in from the community and hope that it snowballs out? Like, given that CAM is a community effort as opposed to centralized, like the UK Met Office. I mean, like, at least start somewhere and then see if you can do it, and if the community takes it up because it becomes a valuable resource. Like,
No doubt it's a valuable resource, but like, you know, universities haven't got time to do this kind of thing. You don't write proposals to do a tech note. I mean, it really is the stuff that NCAR should be doing. But, you know, we're stretched as well. I mean, these are hard decisions to make, and we have to prioritize.
Show up on your H index.
Right,
You know.
we have to prioritize. That's the key thing. Everything we've talked about now shouldn't be viewed as an equal thing. We should prioritize.
Part of the problem too might be, we're trying to distill the knowledge of the inner circles and not, that can't come from outside necessarily. It needs to come from inside.
You know, we started the CAM Wiki, and it's kind of ad hoc, but it's sort of based on, oh, a user asked us a question. Oh yeah, we should write that down. And so, you know, it's not as organized as a scientific guide, but just a way to start getting some information down.
CSM has bulletin boards, and really one of them should be, hey, as someone said, I can't remember who said it now. Hey, this is my configuration, there it is, it's, you know, archived in there, you can do a search of that particular, you know, set up a template to say what you did, resolution, where, etc. And maybe that's just to keep everything in the same place, because stuff is all over the place as well, it doesn't help.
I think creating a resource like that is exactly what a community effort should do, right? Because we're all being asked when you write papers to be more and more clear with, you know, use cases, and of course it's harder and harder to document data, especially on these high res runs that have been shown this week. And so, you know, having a way in which, you know, if you have access to the computer, you can get a bit for bit reproduction if you use this use case, right? And here's all having that be easier to be able to pile off and then in a way in which it's easily read somehow in a wiki, but also could be used in the data section of a paper, I think would actually really, I think that's the new way to do a little bit of, you know, the community effort for a model that's changing and has all these different configurations. And it's not necessarily having a 600-page tech report. I'm not advocating for that. I just want to be clear. But I think it might be. I think it might be a great way to, and also it's a great way to collect data for NCAR, for AMWG, to know what the model's being used for, because it might actually inform the direction that the model takes 5 years from now if we have a repository of all the different cases and what they've been used for in the past.
Well, I really appreciate, I think we all appreciate the discussion and the input. It is 3:10, so we're
we're into our free time, so unless someone has an urgent comment now, I suggest that we adjourn. I think we've gotten a lot of really good input. I want to thank Wei for agreeing to be the co-chair.
Thank you.
And thanks everybody for